Yeah,
Yes,
just
yes, it's on. I see that.
yeah.
Okay, good. I think good morning to all of you. It's very pleasant day and also, of course, pleasant evening to Professor Shivar Banerjee. So we welcome you all on behalf of the organizing team. And first is the panel session, following by technical sessions. This meeting probably the shortest time span genesis is that 15 days back or almost like 20 days back we thought let's have a meeting, and it all happened so quickly, and whoever we requested are very kind, they just accepted our request, and here we are. And I request Professor Rajkumar to say a few words and welcome the gathering and the dignitaries for this panel session, as well as several invited speakers and young participants. Thank you. Please go ahead, sir, and it's up to you, up to Professor Rajkumar.
So, good morning, everybody. I can see who is who in material science present here. Compliments to Professor Satyam for bringing you on board today and possibly for tomorrow also for this meeting. I'm happy to see Professor Sri Kumar Banerjee, Dr. Satyasat Basu, Professor B.S. Murthy, then Professor Kamanio, Professor Deepankar Banerjee, Professor Basu, so Dr. G.K. Day, Dr. Muralidharan, Dr. A.K. Srivastava, and other colleagues present. Friends, as Professor Satyam said, so on this very important topic where the IMMT and CSIR-IMMT joined us in organizing this two-day seminar on electron microscopy related topic, where the exact topic is in special techniques on electron microscopy for material science. Very important technology area, and certainly in the context of the backdrop where, and in the context where our Honorable Prime Minister is talking about Atmanirbhar Bharat, it is important that we recapitulate on the recent developments and make use of these possibly for developing some of these technologies within the country. I'm sure all of you are aware of this fact that the pandemic taught us many things, and it also taught the whole world in some kind of unreadiness to the situation. So the technology development almost throughout the world is absolutely essential. There are at least the emergency equipment and some of the high-end equipment which we cannot wait for long. Formally, I welcome you to this today seminar, and also to, in a virtual way, to IIT Bhubaneswar. It would have been organized on the campus had there been the pandemic and the times been normal, and you would have seen our campus as well as visited IMMT and also the CSIR laboratory. I'm also happy to note from Professor Satyam that BARC is developing some of the electron microscopes and trying to make a difference and start manufacturing in this area. And we're also happy to learn that they are showing interest to collaborate with us. IIT Bhubaneswar is very much ready, and like any other IIT, we also have multiple disciplines, and we are certainly very much determined to see that we play an important role in technology development and contribute towards Atmanirbhar Bharat. In that sense, we are ready to take up technology development, collaborate with other institutions, and like to learn and then move forward collaborating. Certainly, I would like to assure from our metallurgical and material science engineering school that, and other schools, that we are eager to participate in such events. So, coming to IIT Bhubaneswar, So Dr. Murthy is there. IIT Hyderabad has been doing extremely well. So off late, IIT Bhubaneswar has also been very well. We are determined to offer strong academics and work on research which makes a difference. Difference in the technology scenario of the country and even beyond the country. That means would like to develop things. Certainly, all of us agree that we need to do some fundamental research and academic research as well alongside, but we would like to certainly provide extra emphasis to technology that can be transferred. In that direction, we made some significant strides and capabilities we have in our earth sciences to predict cycles 5 to 6 years advance is only one of them. And so on academic front, I said we are offering uncompromised education. We even organized pen and paper normal examinations even last year in April and May to hold examinations for our students. And we are continuing to do similar things. Even during an online education, we are trying to see that the education is as per normal standards, if not better than that. That's the kind of thing that Bhubaneswar has been. I was told that Dr. Muralidharan has been awarded with the Lifetime Achievement Award by EMSI. Congratulations to him on behalf of the Institute and my own behalf. And so with this, once again, I welcome you to this today's seminar and would like to join Professor Satyam in thanking you profusely for making your presence felt on this webinar, wherein a large number of our students are participating. So thank you once again. And thank you, Professor Satyam, for giving me this opportunity to share a few of my foreworks.
Thank you. Thank you, sir, and I really appreciate for being with us. So whenever I just went and requested him, sir, I would like to have it, and he said it's up to you. Just the complete freedom for us to have it. I appreciate it. I think the second person is Dr. Professor Basu. When I have this idea, I said that IIT Bhubaneswar would like to join IMMT in holding this conference. I think I never heard no from Professor Basu for any of these kind of things, and it's very positive coming forward and helping all of us, even having a collaborations with IIT Bhubaneswar is there. So I request Professor Basu, one of the patron of this conference, to say a few words with welcome address. And of course, he later on can also join in the panel discussion. Professor Rajkumar also is welcome to join the panel discussion and be with us as much as he can. And now it's Professor Basu. Yes. I think unmute, Professor Basu, please unmute.
Good morning to all, and possibly good night to Dr. Banerjee and all the dignitaries on my screen, which is a new thing that we have to talk about, and those who have joined otherwise also as a chairman of the session, speakers and the delegates of special technique in electron microscope for material science application STEM 2020, organized by IIT Bhubaneswar, CSIR Institute of Minerals and Material Technology, and EMSI. And this is a 2 days conference. I welcome you all, and we have a special reason to join, which we will come to know towards the end of the conference on 7th, ending with the valedictory session. Of course, the starting is very important. Self-reliant India, Atmanirbhar Bharat, especially we want to focus on material science and engineering and metallurgy. Just to talk about a little bit, our institute is mostly focusing on mineral processing and extractive metallurgy and material development, functionalization of material and related devices. and along with that environmental environmental and sustainability. So this is how we focus and we work on. So this is especially aligned with what we do in our campus and today's conference or the seminar. And I just wanted to highlight there's a hot topic that being discussed last 2-3 days in everybody's WhatsApp about the 2% of the scientists in world ranking, those who are from India. So I was just browsing through, we were doing some analysis. We found that there are about 94 scientists from ISC Bangalore, about 64 from IIT Delhi, 41 from IIT Bombay, 31 from IIT Kanpur, and a similar number from IIT Kharagpur. I don't know about the other IITs, and I can talk about my institute, which I take a pride to tell, from CSIR Institute of Minerals Materials Technology. We have 8 people. 4 are right now, of course, is on working here, and 4 just retired. So more or less, if I take alumni and our scientists together, we have 8 people in the list, which is about possibly about 8% of the total number of scientists that we have fall into that 2% category of world-renowned scientists, which is being tabulated by Stanford, and it came in journal 1+. So 1+. So this is something to talk about, but I also have to tell here that the number for India is not that great. If you compare with developed countries, Europe and America and Korea, Japan, China, then India is not doing that great. So I think this is the time that we need to discuss and we need to work to show that our quality of work, quality of whether it's a translational research, fundamental research, or a commercialization of our technology, I think we have to all work really very seriously, and we have to put our mind. And one of the foremost area that we can really do well, I think the material science and engineering and metallurgy, I think there the India done quite well. I must say that engineering, especially if you see, India has done quite well when you talk about this, any ranking you see, where we are not able to match the developed countries in science specifically, although we have a lot of people in physics, chemistry, and mathematics. I think, of course, they're doing extremely well, but even then the others are doing much better. Basic science in biology, life sciences, physics, and chemistry. I think we need to buck up and we need to work together with this few words, and welcome you again and giving you valuable time in a short notice as Professor Satyam talked about and Professor Rajakumar talked about. I think we are very fortunate that we have all the luminaries of material science and engineering and metallurgy here. And with this, I would end, and we'd start with of course, the panel discussion session. Thank you.
So thank you, Professor Basu, for giving the welcome address. And I request now Professor Srikumar Banerjee, who is the Chancellor HBNI, and more than that, for us, he is like a father figure for microscopy. And along with several luminaries sitting here in this dais, I think our society could survive because of great effort by him and other like Professor Casey, and Dr. Day. So I think this is a great opportunity. We feel rather fortunate, in spite of he being there at the other side of the world. He agreed us and it's very kind of him to be with us. And I request him to inaugurate the today's seminar, and of course he can give his opinion on Atmanirbhar Bharat. The way he likes. And this is for you, Professor Banerjee. I welcome you.
Thank you, Professor Satyam, for your kind words. And first of all, I think this is the first time I'm meeting Professor Rajakumar, though virtually, and it's a pleasure that we are meeting in this format, and we do accept your invitation to visit IIT Bhubaneswar at appropriate time. And Professor Sudha Satta Basu is very close to me because I happen to visit their institute quite very frequently. And next time I go, definitely I'll also make it a point to IIT Bhubaneswar.
Peace.
We also have Dr. Srivastav, a friend to me for many, many years from AMPRI. He's also from the materials, particularly materials processing side. And that's very important. And my friends like Dipankar, Kamanyo, Gautam De, many others. Of course, in my screen, I think 6 of you are present. Many others are there in just their initials. Okay, so now it's interesting that we are talking of Atmanirbhar Bharat. I'm just taking some keywords of your announcement. One side you have Atmanirbhar Bharat. The other side you have electron microscopy. And I was just trying to connect these. Is there any way electron microscopy do anything towards making Atmanirbhar Bharat? It's a difficult question because the challenges in the electron, of course, making an electron microscope, as you said, is a very important point. If you can do that well, just a beginning has been made in SEM, but do it in the, I mean, we should have done it much, much earlier. But since we can build a big synchrotron, we can build nuclear reactors all on our own, then why can't we have a microscope, even an atomic resolution microscope ourselves? So, but that's a different kind of effort, and perhaps there's not so much of commercial interest. And that's perhaps the most important reason why such a thing has not happened earlier. But time has come that we have to think in these directions. And when you do that, don't do something which is next to the best. That is not going to work today. Today, if you have to do anything, it has to be at par or if not better to what is available elsewhere. If that is the standard we keep, then only we can achieve something. Now I come to this issue of Atmanirbharta. And basically, Atmanirbharta depends on the resources. How can you become Atmanirbhar if you don't have the resources? Fortunately, in our country, we are really strong on our agricultural resources. That's why on food, we are Atmanirbhar. We are also quite rich in our minerals. But in providing all the materials that we need, we are not that much Atmanirbhar. Imagine our planners for the first and second 5-year plan who thought of making a big inroad towards fertilizers and steel. In both fertilizers and steel, in steel, you know, though we may not say that we still import quite a bit of high-end steels, but this I've heard from TISCO people that in the hot metal, I think we are competitive to the world from the cost-wise, quality-wise and cost-wise. So we are not second rate, we're almost at the first rate. But our processing somehow, maybe partly because of our energy cost, does not match up with that in many other countries, and that's one of the reasons why we have to still import. On clean steel, perhaps we are not that good. But imagine in things like in superalloys, it is Dr. Tamankar who took the initiative that we must be, in which year? This is around mid-60s. Around mid-60s or late 60s perhaps. Dipankar will know exact dates. But he realized that it's important for us to be self-sufficient in specialty alloys, nickel-based alloys, even refractory metals. See, he took up the issues on tungsten, on molybdenum, and on the other side in Bhabha Atomic Research Center, people were working on practically every element of the rare and refractory side. In fact, I would refer to all of you a very nice article which Gautam De has recently written. I have seen that article as a preview, and that's on what exactly we have done on the rare and refractory metals, all of them. And it's phenomenal that all this has been done with the Indian resources. Whether you can bring that to the final usable stage. And it has been done. Not that everything is commercialized. Commercial interest comes when it is on a different level. But I think the importance of this conference being held in Bhubaneswar has a very important meaning, because you are relating the mineral resources and converting mineral resources to usable materials. And this is a job. If this is taken up as a seriously by laboratories, I mean, 3 CSIR laboratories are present right here, including Muralidhar's CGCRI, who are also doing quite a bit on the indigenization of variety of processes. Like one of the things which you often talk about is on the refractories. On steel, we have a very great ambition of reaching 300 million ton of production annually in maybe 10 years' time. Now, if we are to go to 300 million tons of production of steel, we need refractories also, and refractories today, particularly high-end refractories, practically everything is imported. So this is a big task that we have in front, and we have people like Murali. Of course, he has just superannuated and is now shifting to another very important area, that is electronic ceramics. So that's yet another area where we are very much importing, and it is possible for him to contribute in these directions. Okay, this is one side of the story. How do electron microscopy connect with this? See, some of the things which I wish to do, but I could not do. I'm just telling you a few examples. From the very early stage, maybe late 70s, I was thinking, why can't we do some very detailed study, not in macro level, but in almost atomistic level, on gas-metal reactions. Long back, I saw one paper, very interesting paper. He took a piece of hematite and take that hematite slice and then try to reduce that with hydrogen. So imagine and if you see, if you are doing the reaction in gas reaction or gas liquid, I think electron microscopy don't come in directly in those kind of studies. But if you take up a piece of hematite and reduce it by hydrogen, from that iron will come out. Of course, it will come out in the delta form and it will go through the transformations. And then if you look at that structure, it's extremely exciting structure that one side you have hematite and there's a reaction front, and across that you have a metal which is reduced from that. And the crystallography of a process like this can be studied. So now this is rarely studied. Even today, I don't think you'll find even 10 papers, not thousands, because there are people who are worked on, but this kind of thing is not done. But it is very much likely. In case of hematite to iron, the crystallography may not be as interesting as in case of refractory alloys, refractory materials, particularly, say, let us take niobium. If you take niobium oxide, niobium pentoxide, and reduce it by hydrogen, you'll be having various suboxides. And the interesting point is that the suboxides are as if these are different steps in the process of reduction of different stoichiometry. Crystallography also, there are successive ways of transforming one structure to the other. One side there's a stoichiometry change, the other side there's a crystallographic change. And each of these are exactly following each other, and they'll be almost like parallelly happening. And this is a wonderful subject which I remember long back, Ameling's group used to work on some of these things, not in so much detail, because their interest was mostly crystallography. But if we find that, like Professor Suddha Satta Basu has a lot of interest in using some of the advanced techniques in material science, in mineral processing, in materials processing area. So this is wonderful topic of that kind of study, where we can use the present day techniques in resolving some of the issues which has not been taken up because it's not a fashionable subject. Commonia will take up only fashionable areas. We will not touch this. There are many others. So if you choose topics like this, which are neither classical nor very fashionable, but these are interesting. And not only interesting, this may finally lead to something outstanding, something totally original. So I was thinking that the minerals, materials, and electron microscopy, they can be linked. I'll just tell you one or two small things because I've been given only 5 minutes time. I think I've already covered 5 minutes. So the next important point that comes here is that a few techniques. See, earlier, doing a good electron microscopy if you take transmission electron microscopy, requires making good samples. And if you take anything on mineral and all that, only mineral I have seen that people used to do some kind of a fine particles and looking at the particle, whether the particle structure, these kind of things, not even a good petrography work, which could be done. Because geologists have done it to an extent, but it could have been done in much greater way. But today, by the focused ion beam sectioning technique, it is possible for you to pick up a very small area from a sample which is compositionally and structurally heterogeneous. At the same time, it is possible for you to pick up the right place by doing a systematic SEM work on that, and SEM coupled with EBSD, you can actually do both crystallography, compositional analysis, and morphology, and then pick up a right type of area which you can do a detailed electron microscopy going right up to atomic level resolution. So this kind of a connectivity, if we can establish in any study, I think there is the subject becomes very attractive. So this, I believe, is a very important way of connecting the material processing towards. And processing, of course, has now many dimensions. Like if you again go to IMMT, they have a wonderful facility for the plasma-based processing. Similarly, processing of electron beam, processing by different ion beam structures and variety of things like that. The other important aspect which is becoming very much important today, even in making good publications, is to combine techniques. And if you do good microscopy, it's not enough. You do good microscopy, you can take the same thing over to a synchrotron and do an analysis where you can, perhaps you don't get that much of a spatial resolution, but you have an excellent both crystallographic as well as spectroscopic resolution. And so you can actually get many things. And then a TM, you do yields. Yields is what you can do in a synchrotron. You can't do the same level of yields in a electron microscope, but it is possible for you to find out what's the chemical state of a particular sample volume, which could be as small as a few nanometer cube. So these are the new trends which are opening up, and here again it's a tremendous possibility. I recently had some experience here too. One of them is on cast iron. In fact, long back when I saw a book called Physical Metallurgy of Cast Iron, I was intrigued by that, but didn't get a chance to work on it. But later on, in coming to the University of North Texas, I had an opportunity to work on cast iron and doing TEM of cast iron. Now, again, I'm referring to Communio. Communio will say that cast iron was discovered 2,500 years back. Why are you waking up to do that today? So answering that is that it might have been really discovered and utilized 2,500 years back. But even today, there are challenging things that you can do in cast iron. And that I was very pleased to do that work. And recently, just in last couple of months, was working on alloy 718, a very interesting alloy on which, again, Dipankar will be very familiar. The alloy 718, which is a gamma double prime strengthened alloy. And that with the processing in additive manufacturing. So combine additive manufacturing with high resolution microscopy. So you can get, this material is now in additive manufacturing. It's a very fashionable subject. But I have not seen many papers which says that additive manufacturing does not produce a homogeneous material. Additive manufacturing inherently will be producing a material which is a cast structure. It's like a weldment structure. So that has a tremendous variation in composition across in microscopic length. And so if you can actually study this in detail, you find wealth of information, much different from homogeneous alloys with which we are familiar to. So there are opportunities. And these are definitely possible. And today with the combination of, and also the interest in the I think there are, Gautam will know better, but I think there are six titans are already there in the country. Is it 6 or more, Gautam?
Gautam is another line. I think we have more than that.
Oh, more than that. So we have that. So there is, if we talk of that.
Bangalore itself has 3.
So insufficiency, no, all of them are perhaps not committed to doing material science research, But I would say that there is not much of deficiency on this, but each of these requires painstaking work. None of these are straightforward. None of these are like you have an input-output type of a process. No, it takes time. It takes time, it takes patience. And if you do that, I'm sure that these kind of work will. So there is a big contribution that even very, very basic science in metallurgy, minerals, mineral processing, material processing can do as a very good science, and it can be linked with the technology development. Talking of technology development, I wanted to remind you one very important point. You see, when India started on the nuclear energy program way back in 1950s, at that time, some famous geologist was with us, and the Jadugoda ore was discovered, but it was known that India has a very poor quality of uranium mineral, as low as 0.04%, whereas worldwide you have plenty of uranium. And imagine in 50s or 60s, there's no hurdle. You can as well buy from any other place. So Baba could have decided that why bother about opening a mine in India, which is so poor in quality. You can't compete internationally. So you can as well import. Had we done that, what would have happened? We would have become totally dependent on others. Our sovereignty in the nuclear area would have been lost forever. So it's just that decision that in spite of our mineral, much poorer means even it's much more expensive. Even today it is much more expensive compared to the international market. But being Swanirvar, we have that sovereignty over it. We have the freedom of using it in our own way we like. So it's extremely important, not only from the economic point of view, but also from strategic side, that we must have. And strategy does not necessarily mean military strategy. Strategy means everything. If we have to be independent, we have to have our own resources, our own technique of processing them, and our own way of technology development. Sometimes not even best commercial option, but best commercial option need not necessarily be in the long run the best option that a country has to take. A country of 1/5 of the humanity has to take some decision that we must be sovereign, we must be independent, we must be self-sufficient. And that is the spirit behind this meeting. So I definitely congratulate Satyam and all those who have joined him for making this meeting possible, and where you are getting a very large number of good material scientists to come over and giving their ideas on this topic. So with this, I've exceeded my 5 minutes, I hope. Thank you very much.
So, thank you very much, Professor Banerjee. It's always a great pleasure, inspiring, and we get a lot of energy by hearing you. And in this seminar, there are a lot of youngsters, a lot of students from IIT Pune or IMMT also attending, more than 200 people. And I think these words will really ignite them to take the challenges. You actually try to connect it from conventional to the problems which are there even in manufacturing, taking the technology ahead, and also the importance in the strategic. I really appreciate. Of course, I'm too small for this, but I really thank you for spending your time despite being the other side of the time zones, and I really appreciate for your time. And naturally, Professor Srikar Banerjee is there, and then Professor Kamaneji, they'll always be there. And now I request Professor Kamaneji to say a few words. Professor Kamani, I think your video is off. Probably you are on. I guess.
Okay. So, before I start, it is always difficult to talk after Srikumar Banerjee and his many punchlines, sometimes directed to me. However, before I start my 5 minutes of Srikumar Banerjee's standard, which may be 10-15 minutes, I must first, my mind actually went back to my BHU days. because this meeting was connected with Muralidharan in certain way. And 60 years back, actually, I had the privilege of, not 60 years, but during the final years of Muralidharan's batch, I had the privilege of teaching them, interacting with them, and this was a wonderful batch. I now wonder that Muralidharan is superannuating, Madan Gopal is superannuating. I understand that from Tata Steel, this Sanjay is superannuated, so time flies by. And that time I remember that we used to talk that this batch, people of this batch will make market for India. And they have really done that. So I am very pleased, and all of us who were in BHU at that time, all of us will be very pleased to see the progress. Now coming back to the Atmanirbhar Bharat, the title of this talk, my take will be always a little bit different. Atmanirbhar Bharat is not a new thing. From the day I was studying, I remember Indira Gandhi's times, and every government, every different period, and particularly different period of crisis, people are talking about Atmanirbhar in a different terms. It may be indigenous, it may be national interest, but everything revolves around one concept, that a country of such a large number of people cannot depend all the time in outside, and therefore they have to develop things on our own. So this concept is very simple. That concept to talk about by a politician or an administrator or a policymaker is very simple. But implementing them is not that simple. My entire career now, when I looked at it, I realized few things, because every turn of events of my career, I face these questions. What are you doing? Is it relevant for the country? Why don't you do something useful? So I like to share my views on it. Every engineers, every scientist, when they do something, they want those things to be used. Because after all, we are doing it for humanity, and humanity is not a vague term. Humanity in our perceptions, the people around us. Because we cannot really feel for people whom we have not seen. So that question should not be asked for any of the people who are working on science, because every one of us want that. Then why we cannot do it? So many things. Why people in the United States or China or Russia, they are developing things which we find it difficult to develop. To me, there are three stages of Atmanirbhar Bharat, as I see it, from our viewpoints of a scientist, viewpoint of who are working in scientific laboratories, scientific academic institutions, who claim that they are scientists. The first one is our own work in different areas that we do. And there is no compromise there. You can, as I think Sukumar Banerjee has told one small word, which I think may have been lost to most of you. You cannot do a work, whether you develop ACM or whether develop anything, you cannot be second to none. You have to do things at the cutting edge. Most of Indian scientists, most of my colleagues, when they try to interpret Atmanirbhar Bharat, they forget this word. And in a way, they start following things, or somebody comes and that we don't have this, so you start working that, which is already done somewhere else. So it is not really cutting edge. You are not going to get our country ahead by doing a routine repeating work. But then if you do something very exciting, can we also have the, will you have also have the responsibility to take it to the actual techniques? Because nowadays in DST meetings and other things, questions is often asked. How do you connect it to industry? What is the industrial thing that you will do? I think even my recent experience where I thought I am working on things which are directly relevant to this country, not immediately, but in future, new alloys, new aluminum alloys, new cobalt alloys, which has a high promise. I have been asked in some of the reviews, not by everybody, but few, why don't you go to GTRE and make a component for them? Completely forgetting that there are processes involved before you make a component, and making that component is not our job. Therefore, the thing that I have felt is that even if when you are doing something which is very exciting, where India can be a leader, still there is a stage where this has to be taken into a different level. And that different level can be done by people in national lab, like what we have in US, or industry, and then it goes to the industry. There are processes. That process has to be set up. Now, coming to this, we do have several places, but we do not have an intense process that these countries have. I don't blame people whom we say that, oh, well, they should do it, because this is an ecosystem. If you look at abroad, this middle level where technology, a concept is transferred to a technology, this middle level is driven by either strategic initiative of the government, like ORNL, or like a Los Alamos lab, or by companies who want to develop that technology, plain and simple, to make money. Now, in an industrial scenario, till now, it may be changing a little bit, it is changing, where making money is simpler by getting a license from a company abroad and producing it here, may Sukhoi aircraft, may it anything else you think of. I think this will not happen. Only when our companies become multinational, our company will be denied licenses because they are competitors. This is going to happen. And it is happening in a small way. Like now we have at least 2 or 3 companies who are multinationals, who are competitive, like Tata, like Reliance. And over a period of time, they will have a drive to create that middle level. And only then you will have a real connections of these chains. Otherwise, it will not. It will take time. It is happening. It is slowly moving towards that directions, but it will still take time. Then the question comes, then what will we do, people like us? Shall we wait? Of course not. We must do the very best. We must innovate. We must do new things. And we must develop things so that there's a palette is available when these things happen. There's so many new things that generate in this country, that people are working in this country, that when somebody wants to do something new, they find, oh, here is the person. And that call will come from the other side. They will seek us out if we do really new things, if we really do cutting edge things. Otherwise, things will not move. But that call has to come from them, but that will come only when we do something exciting, something which is new, which people realize that new and we can do. I'll give 2 examples of my recent experiences, and then I think I'll close. First one is when we were setting up the Titan microscope. We realized that we do not have a money for getting the room ready because there's a lot of technology that is required to make the room ready. And the cost that is quoted by our European vendors is almost same as a new microscope for putting those technologies in. So I went to my professors. That time I was a dean, so it was easier, and I had a friendship with a lot of young, bright assistant professors, and said that, look, I am in this sense, can you develop this? And at least 2 of them said that, professor, we'll do it for you. And it took about 8 months to 1 year, starting from fluid mechanics simulations of airflow to actual designing of the things and getting it done. And we have in our microscope room, we have a technology that has been put in, which is at par with anything, anywhere in this world. That's fine. But that stops there. I tried to connect with few companies, but there is not enough volume for them to get the technology and take it to a commercial level. And recently, when I was looking at the IIT Jammu installation of the microscope, Geol has set up a subsidiary company which exactly same technology as we have, exactly. And they are marketing it all over the world. So this I highlighted because the difficulties that we can have, that we can do something in our small university circumstances, but taking it out to the world or to a commercial level is difficult. Second thing is more positive. Last about 7-8 years, we are working on aluminum alloys, initially funded by Boeing, a very large funding. And Boeing just gave us a challenge that, professor, you just try. I say it's impossible to do. They say, you just try. If you cannot do it, we'll write it off. And obviously we failed. And they said that we are not taking back the money, but we are closing the project, but you use that money and continue to work. Then we succeeded in developing a high temperature, high strength alloys. And this is there all over in the papers and other things. And then a company comes to me because US has developed, there are a few companies, venture companies, who are marketing what they call it aluminum super alloys. And therefore, this company, Indian company, came to me and said, professor, can we develop it as an Indian alloy? So I wished I can do it, and now that we have come, let's do it. Unfortunately, Corona came and auto industry went bust. And this is a middle level auto ancillary company, so I could not proceed. But it can happen if we do something new, if we can keep it everywhere, people will have a knowledge, people will be attracted to it, and when time comes, people who are hungry for those technology, they'll come to us if we are ready. So for us, I think that's the pathway. So we must continue to do things exciting, things new, and then hope that someday we'll have that handshake and it will be really be fructifying. Thank you very much for this opportunity to talk to all of you.
Thank you, Professor Pawan Chattopadhyay. As usual, these are very interesting topics and also challenges given to us. Now, I request Dr. Basu. I think he spoke on welcoming, but if he has something to add, because as a part of Atmanirbhar, whether you want to say something further, we'll come back to all the panelists. Mr. Basu, you'd like to say, as per the program we have here.
Oh, you are you are talking about D Basu or S Basu?
Only S Basu, the panelists only you are there. So.
Oh, okay. So once more, I just wanted to say a few words about the Atmanirbharta perspective from Institute of Minerals Materials Technology. I think I would like to focus on mineral resources of the country, and there is so much of important mineral deposits are here, and we can easily use them for different purposes. Sometimes because of globalization that happened in 90s and opening of market and the competition, we, as Professor Srikumar Banerjee was talking about, that when the price is lower, we go for it. So we keep on importing many important minerals to our country, and now time has come that this pandemic situation showed us that with the disruption of supply chain, with geopolitical scenario changing, there is so much of importance that you have to be self-reliant or Atmanirbhar in, at least in some strategic area. You really cannot depend on others on those areas. But starting with, although iron is not supposed to be a strategic mineral, but even if we go for, let's say, the benchmark that we are looking at, 300 million ton of steel by 2030, even we say we cannot do it by 2030, that doesn't look like feasible, but at 2035, if you have to get 300 million tons of steel, then where you require about 800 million tons of ore. Where are you going to get it from? This is all per year, per annum basis I'm talking about. Where are you going to get it from? There is no way you have to use your own resources. That is a low-grade iron ore that we have. And if you use low-grade iron ore, the technology could be a little different than what we are doing today. So low-grade, as low as 40%, 45% of iron content in your ore. IMMT has developed technology to reduction roasting, pelletization, magnetic separation. So this reduction roasting technology for low-grade iron ore, not only that, we have a lot of fine sludge lying in the plant. I mean, this could be a huge quantity. These are like a mountain of slimes, fines, and sludge is in any steel mill. Lying unattended, this could also have about 50 to 60% of iron. So we have this technology, which of course is very profitable, and I must say that JSW, Adhunik Steel, and now ArcelorMittal, Adhunik Steel is already decided to put that. JSW is now looking at an area for putting the plant. ArcelorMittal has taken the technology. They are also interested, formerly SR Steel. And not only that, we also come up with a technology that using coal. Coal is another thing that we get a coking coal. About 50 tons of coking coals are being imported every year for steel making. So coal is another area that we need to work on, because we have a lot of deposits of high ash coal. And generally, you require very low ash content coal for your blast furnace operation. So we have come up with a fluidized bed roaster where we can use coal gas. I mean, making coal gas from a high ash coal with clean coal technology, with a carbon CO2 sequestration, and use that coal gas as a reducing gas for in a fluidized bed roaster for conversion of low-grade iron ore flying slimes and sludges to iron. So these are the technology which is quite useful if you talk about going for 300 million tons per annum by 2030 or 35. The other area I want to touch, because other critical mineral area that I want to touch is about tungsten, lithium, neodymium, or all rare earths for making magnets. So I want to talk about the tungsten and lithium. These are here also. I think mostly we will be looking at urban mining. We do not have tungsten and lithium sources. These are secondary sources that are available, of course, and urban mining is the other way to look at it. Of course, if you acquire mines in different places of other countries, then of course you can. There's the strategy, and we are already acquiring mines in Africa, Congo, and Ethiopia, and all the other Central African countries. And that's the source for even cobalt, manganese, copper, nickel. We have these. Cobalt is another resource that one should look at it for the lithium-ion battery, and if you have e-mobility coming up, about maybe about 30 million vehicles by another 10-15 years to be added. I think cobalt, the lithium-ion battery based on cobalt, nickel, manganese. Manganese, we have a lot of deposits, and we are working. We have developed a technology for MOIL. MOIL is going to ramp up their production from 1,000 ton per annum to 1,500 ton per annum, which is going on right now, the commissioning. And then they have a plan to go for 10,000 million tons per annum plant will be coming up just outside Nagpur. So these are the technologies for cobalt, for the cobalt scrap. Again, I'm talking about from the scrap or from the secondaries. We have given a technology to Bidhani. Manganese for MOIL. Copper is, again, we import good amount of copper. We are not self-sufficient in copper. Nickel as well. So these are the things we can still do it because we have the resources of copper and nickel. We have a big chromite overburden here in Odisha where nickel is there, and there was technology developed in IMMT. There was a plant running at IMMT long time back, of course, because of the pollution control CPCB's directive, we have closed it. There's a hydrometallurgic route. So, and then of course the rare earth from urban mining, rare earth from fly ash and red mud, that we are all working six conglomerates or 6 consortia that we formed: NALCO, Hindalco, Vedant, NML, IMMT, and JNA DDC. We formed a consortium, and we are going to get all the valuables from rare earth, including iron, alumina, titanium, and then scandium, and then there are other rare earth also present. Neodymium, we are working from getting a 4,9 ND because of NdFeB magnet. Nd2O3 is plenty available with IREL, but we do not have a technology to get pure Nd. We have calcithermite route done by BRC. There is a route on chloride route done by NML, and IMMT did the fluoride route. Fluoride route is the best in terms of getting a 4,9 ND. Of course, you have a less cost because of we are doing a salt electrolysis. So these are the areas we are working, I think, and this is perfectly fits to Atmanirbharta that Honorable Prime Minister talked about. And I think this new thing emerged because there was a globalization, and we thought that we are one world, one nation. But when the pandemic comes, then we understood that you are on your own. You have to do on your own. There is a supply chain disruption, and you have to fix whether it's a medical device or medicine or whether it's a PPE, anything you talk about, you do not have the resource to get, you do not have that the funding resource to get everything from outside or get imported everything. That is how this concept come up. And then we realize now, at least in certain sector, we need to be Atmanirbhar, we have to brought the Atmanirbharta, and that is how this has come up. I think that's a good initiative taken by Government of India. And with this, I conclude. And I think IMMT in this in mineral sector and critical mineral sector, we can really do a lot of contributions, and we're already doing it. That's true. My predecessor, Professor Kamani Chattopadhyay, already mentioned that we are doing it because many people will not understand that in mineral sector, India is quite good in terms of self-sufficiency. But there is also scope, as I said, especially coal and iron, which is huge quantity we are importing. With this, I conclude, and I I'll thank all of you for giving me this opportunity. Thank you.
Thank you, Professor Basu. And I think the importance of mineral processing is important. I think just besides you, we are here in IIT Bhubaneswar School of Minerals, Metallurgical and Materials Engineering. We'll also join your hands, already joined with MOU with you. I'm pretty sure with the high students. Actually, there are about 100 students from the school are attending this conference as well. I think your talk inspires them about the mineral processing. Pretty sure as a good one of the best academic institute will be working with you on this. So now we move on to Dr. V.K. Srivastava, who is the president of AMSI. Actually, when we wanted to do this conference on behalf of AMSI, you readily agreed. Of course, is a friend of mine for several years. We know each other, and he also happened to be the director again of the similar materials processing, advanced material processing research institute in Bhopal. I request him to speak. Welcome. I request him to welcome on behalf of AMSI and share a few words with you. Thank you. Please, Avinash.
So, good morning, and also good evening to all. Please accept it in your best possible way, wherever you are at present. On lighter side, Professor Satyam did not give me flexibility as he gave to Professor Basu. But anyway, thank you for inviting me here on this platform. On behalf of Electron Microscope Society of India and CSIR Advanced Materials and Process Research Institute, Bhopal, and also on my personal behalf, I welcome first today's chief guest, Professor S. Banerjee, Chancellor, Homi Bhabha National Institute, and also former Chairman, Department of Atomic Energy, and also the former Director of Bhabha Atomic Research Center. And I thank Professor Banerjee for kindly agreed to inaugurate this very important online seminar on special techniques in electron microscopy for material science applications, STEM 2020, during 6th and 7th November 2020. I also take opportunity to welcome and thank all dignitaries, Professor R.V. Rajakumar from IIT Bhubaneswar, Director, Professor S. Basu, CSIR-IMMT Bhubaneswar, Director, Professor Kamani Chattopadhyay, we all know him very well from ISC Bangalore, Professor D. Banerjee from ISC Bangalore, Professor G.K. Day from BRC Mumbai, Professor K. Muralidharan, again my old friend. I know him since last about 30 years. Professor B.S. Murthy, IIT Hyderabad. I mean, nobody requires introduction of any of such great dignitaries. And we are all well connected since last several years. And all speakers, chairpersons, and participants, I welcome everybody for this today's conference. Last but not least, it is my earnest duty to acknowledge and thank the organizers of this event, in particular Professor P.V. Satyam and his team from EMSI East Zone and IIT Bhubaneswar, and IIT Bhubaneswar and IMT Bhubaneswar, and EMSI in general. With this brief note, thank you all, and once again welcome you for making this event happening, even during this pandemic situation. Now my second part comes to talk a little bit about Atmanirbhar Bharat. So many things are talked and very useful, important topics are touched, whether it is related to microscopy or it is not related to microscopy, but definitely topics on minerals, materials, and electron microscopy are touched. In short, at AMPRI Bhopal, it's a materials processing lab, and we are dedicated for developing advanced materials for in various sectors like smart and functional materials, radiation and free and cement free concrete materials, nanostructured materials, lightweight materials, and waste to value added materials. My friend Professor Basu also touched some of these topics. Now I'll come directly to the microscopy where we are concerned about becoming Atmanirbhar or self-reliance. So first of all, I'll just discuss about 2 points because of the time constraints. First of all, we need to see that as far as electron microscopy is concerned, how do we like to become Atmanirbhar? Somehow it still appears to me, at least to me, even after having so many electron microscopes and some with the highest end specifications, the quality of micrographs and the optimum utilization of the microscopes, it still requires improvements. There are very good attachments like eels and all Professor Banerjee talked, and we have to use these things very extensively for various kind of, even in material science allied developments. And for that, that means the number of operators and quality of operators and hands-on training and similar such type of components needs a special attention. Maybe from EMSI side or in general from the material science community, it requires attention, and we have to take these things very seriously. As I was hearing, and I also know that more than 6 or 7 titans are there in country, and these are very high-end equipments, ultimate equipments in the field of electron microscopy, and very costly equipments. So we have to think about that. Professor Kamanyu Chattopadhyay touched some of these things in terms of the quality. Then another very important desire in this direction is the manufacturing of equipment. Again, this topic has been touched. The manufacturing of equipments, their components, etc. Although in compartmental mode, it is already discussed that by now capabilities are shown in design and development of scanning electron microscope by DAE, CSIR, and maybe some other organizations too. Probably an approach to develop a marketable product, which in other words, it has been told that high-end specifications, quality should be at par with the available products. So that's what I am saying, marketable product with a sustainable model in synchronization with an industry is missing so far. Again, Professor Chattopadhyay has touched this part. The industry has to come forward to take our science or technology to go to the market. Otherwise, even if you see, even in small countries, as I am told, like South Korea, is having 6 or 7 manufacturing units of SEM with different company names, which I am sure will be generating lot of revenue even for the country. Moreover, if we have such companies in the country itself, it is probably easier for working on instrumentation side of microscopy also possible, which will again in turn help us in exploring various fundamentals aspect in our respective areas of research. Because then we can demand that this is our requirement as a scientist. What do we require from the equipment? Otherwise, what is happening? Whatever we are getting the equipment, our science research is constrained. That okay, from the instrument we can analyze only these things. So our research is likely slightly directed based on the equipments what we have. Of course, while developing marketable quality products, the cost is also important, and that is where, as a previous speaker like Professor Chattopadhyay says, that we industries have to become multinational industries. then only this is possible. So quality and cost both are very important. And definitely when design and development part is there, we scientists have to take up this initiative in different levels. Even MSI as a whole can take part in this. So with this brief about self-reliance or Atmanirbhar, thank you all for listening me. Thank you very much. You are mute. You are mute, Satyamji. You have to unmute yourself.
Yeah, so Dr. Avanish Srivastava, thank you very much. So I think so also kind words regarding the welcoming address. So developing the SCM is actually something which we are already working, and we'll talk to you also regarding the society, how much you can do. So I don't know whether Professor Murthy, are you around? Professor B.S. Murthy?
Yeah, I'm here. I'm here.
Okay, so welcome to the.
Sorry, friends. There was a SERB meeting with Professor Manna as a chairman was going on. I just left that meeting about 5 minutes back when Professor Basu was talking. That is when I joined about 15 minutes back.
So welcome you, Professor Murthy, and as I discussed, so please give your views on the today's program and today's panel. Thank you.
Thank you, Satyam. Thank you, Avanish. You are talking about. I missed the talk of Kamanyo, but quite a bit of it Avanish has pointed out. Some of my thoughts are in similar direction. You know, many of us who are sitting in this are users of microscopes for even decades. We all, I mean, at least I can say I started somewhere in '86 or so. So many a times we feel that most of these things we keep on importing. Okay, I mean, including a small thing such as a disc punch, 3 disc punch. I used to think why we should buy from Gatan, which used to cost about 1.5 lakhs or so. Those days, now I do not know what it is. And we were always not finding, even a jet polisher for that matter. Okay, forget about microscopes. Okay, even the sample preparation techniques such as this, a Dimpler, for example, these, in my view, are not really highly electronic dominated. Okay, these are mostly mechanical instruments with a bit of electronics in terms of measurements. I think somehow maybe it is the way we grow up is a problem. Because most of us, at least our generation, the next generation is possibly definitely better. We were not allowed to touch anything at home, maybe a transistor or a TV by our parents, because they were worried that if it breaks, then they cannot afford to buy one more. Okay, that is where possibly we all started, which you don't see in other countries so much. So and also even in our courses at the BTech level, very little of instrumentation is taught to us. Okay, opening up of a furnace, for example, we are all, quite a number of people are metallurgists here. Open a heat treatment furnace and reassemble it, kind of thing is not taught. How many mechanical engineers actually can open their their scooter and reassemble it? I really don't know whether we are in that. So that is something I think should be inculcated from our BTech days from the beginning. Is somehow that's something which some of us are trying to bring in each of our institutes. I know Rajakumar is there, and we are also trying hands-on. So I am ensuring, at least in Hyderabad, that everything goes as far as possible hands-on. And that is something, if we can start doing it, then I think 10 years down the line, we are able to generate a new generation which can do a lot of innovations in terms of developing products. And a lot of emphasis on startups is happening now. You will see that. And that is also another thing that would help people to come up with products. That's the only way. If you want to do carry on with this slogan of Atmanirbhar, what we have to inculcate in our students is the capabilities to design things, capabilities to fabricate things. Okay, that is something that we should inculcate into our students. Even I think Avanish was talking about earlier about even microscopy, for example. Quite a number of students, they are all users of microscopes to some extent, but not really a high-end users. Okay, even many of the institutes do not have something like a practical electron microscopy course. Something at IIT Madras we introduced. I think I'm aware Kamanyo and Vikram Jairam at IISc did it, but every institute does not do this. Okay, so that at the end of a year, you should be able to generate 5 to 10 students who are have the complete capability of doing a high-end microscopy. We need people like that. Also, is another thing that these are all at the academic level. People should inculcate this among the students so that people, the generations that are going to come, should be trained to not only do a high-end microscopy, but also to be able to design microscopes and microscope related equipment and bring them out. Of course, we need support of industry, no doubt about it. But one thing that I have seen thanks to this COVID is the speed at which people are able to do things, starting from a material to a device to its testing and industry coming forward. There is positiveness that I see more and more nowadays, that industries are coming forward. Quite a number of products are coming up which are very high end. For example, I am aware of certain ventilators which have come out in recent times, which are of some of the best in terms of their technical capabilities when compared to many of the imported ones. All these are happening within a span of 3 to 6 months. That tells that there is capability that is available. Only thing is bringing them together is something that if we can all do it, and I'm sure we have the capability to do that. And of course, a number of other areas related to materials, there is a lot of work that needs to be done. Waste to wealth, somebody pointed out. That's another area where there is. In fact, we started a master's program on e-waste management at IIT Hyderabad. We started a program on additive manufacturing. That is another area which needs to be strengthened a lot. And that is something that can help India to grow in a big way in the direction of Atmanirbhar, because additive manufacturing is something that can bring in products in a much faster way. Another thing that possibly some of you must have touched is the computational capabilities. That is another thing. AI is taking a very good shape nowadays. AI included into the ICME, for example, so that we are able to shrink the time that is needed to come up with a new product is something that we need to strengthen and enable our next generation students and people who are going to come up with this kind of a capability, so that we are able to design things and develop things at a much faster base with the help of the computational tools that are available is something that I feel all of us should keep it in mind. And more importantly, one area which needs a lot of strengthening in my view is healthcare. Healthcare with materials as a base where many of us can contribute, particularly in terms of the implants, for example, or various products for healthcare. Thanks to COVID, this is taking a kind of priority in the minds of the government also. So a lot of people are coming up with interesting products in the healthcare, and where most of us material scientists can contribute significantly. Of course, it needs strong collaborations between academic institutions, R&D labs like AMPRI, IMMT, and of course, industry together. But I think we have good time in the years to come, where there is an urgent need being felt by everybody, and we should utilize this opportunity and come together and do a lot of good things. This is what I just wanted to share. Thank you very much, Satyam.
Thank you, Professor Murthy, and we really appreciate your kind words. Now we go to Dr. G.K. Dey. Is Dr. Dey around?
He was also with me in the other committee. I hope he has left that.
Yeah, so I changed my hat and I'm back here. Yeah. Good morning, everybody, and good evening or almost good night to Dr. Banerjee if he is still there. Keeping in view the occasion on which the seminar is being held, it is to honor my old friend Dr. K. Muralidharan. Murli and myself, we are from the same college, that is IIT BHU, and we were very fortunate to be there at the time that we were, because it's at the one of the best faculties in the world at that point of time. Distinctly benefited from that, and not only we did BTech from that, we did our PhDs from that institute. So that is our togetherness as academic level. And subsequently, we parted ways. He joined defense and I joined atomic energy. But we did interact on several fora. And finally, the interaction peaked because of our common interest in microscopy. We belong to the old generation of microscopists, repair the microscope and then use it and then get results. This brand of microscope is of course now on the wane, and we have a new generation of microscopists who probably use it. I'll just leave it at that. And he became the president of Electron Microscope Society after I relinquished. We were trying to revitalize the society because it needed that. It lacked several things, and I could do it only partly. It was Dr. Muralidharan who actually did most of the rejuvenation and brought it to a very healthy level that we see today. After that, it has progressed by leaps and bounds. And then the association did not end there. He took over as director CGCRI, and then I just happened to be in the research council of CGCRI. So we kept interacting at various meetings, and now he is going to change his hat. I won't say he will ever superannuate. He keeps changing his hat, going from one place to another, from defense to CSIR, and now he's again probably continue in CSIR only. So I wish him all the best in whatever endeavor he undertakes. So that is one job I had, and then now coming to the next job of Atmanirbhar Bharat. I will confine to electron microscopy. There are two aspects to it. The electron microscope use in making Bharat Atmanirbhar, and this I will tell from my own experience. We in the atomic energy have been Atmanirbhar not only now, we have been so since the first nuclear explosion in 1974 or so. After that, we were put under severe embargo, and that kind of brought the best out of us, and we slowly became Atmanirbhar in practically everything. And I must admit here that the electron microscope played a very important role in making us Atmanirbhar. There are two things. One is alloys which we use. So alloy, the nature of phases, what should be the phases, what composition, what crystal structure. And that is where the electron microscope chipped in. They told us what should be the nature of phases. We don't want undesirable phases. So that the electron microscope was indispensable in deciding that. And when making the finished product, it goes through several stages of processing. At each stage, the microstructure changes. And that is where the electron microscope came in again. We were successful in developing the flow sheets of many products thanks to the electron microscope. And the principle was very simple. You have a benchmark alloy, you look into the atomic arrangement of that and try to reproduce the same atomic arrangement in the indigenous alloy. And if you have the same atomic arrangement, there's no reason why your product will not have the same properties as the imported product. And this is where the electron microscope played a pivotal role. So the contribution of electron microscope in making us Atmanirbhar has been immense. Now coming to the last part, that is electron microscope is Atmanirbharta, whether we are making electron microscopes in the country. Now, the first transmission electron microscope of Asia was actually made in India by Professor N.N. Dasgupta way back in 1948. Now, Japan is the leader in transmission electron microscopy. But I was pleasantly surprised to see that the first transmission electron microscope was actually made in India.
Satyam, we lost him.
There is some issue.
Your picture is frozen, looks like.
Yeah, I think signal problem somewhere.
So I think in the 1948 we got the TM, and then there was a stop. Looks like this is also like that. Dr. Dey, are you?
Professor Satyam?
I'm calling him.
Please call in. I will also, I have to little bit away for this, from this. I have another meeting.
Yes, yes.
So I'll just come back again.
Yeah, please. And also that I think before we move to final people, and I think Professor Deepankar Banerjee will be giving a summary of this. I would like to see whether Professor Rajkumar would like to say something before.
Yeah,
That's
so it was a pleasure welcoming everyone in my first instance. Let me share a few thoughts, just a couple of issues on my views on Atmanirbhar Bharat. Yeah, Professor Siddhasattva talked about, yes, the supply chain issues during pandemics, geopolitical issues during pandemic, certainly, and even otherwise, geopolitical issues would come into picture when sharing technologies. Though we feel that we are a global village, and it is not necessary that every country masters everything. So since the markets are global, it's a global village kind of situation we have here. It is not necessary. But we are 1.35 billion people. We are a big market. Maybe when Indians use technology, we are more than 3 times the market of the United States itself. So since the economy and 1.35 people's needs are 35 billion people's needs are there, certainly we have a good scope for electron microscope. I'm sorry, good scope for Atmanirbharta in many areas and certainly in strategic areas. About 20 to 25 years back, so Mr. Mursole Maran was the minister. We were discussing about whether we need a fab facility, semiconductor fab facility. And the plus and minus points are there and were there, and these points would come into picture, and investment and then return on investment would also come into picture. Okay, such issues are there, and again we have, as I said, 1.35 billion people are the market, and as a technology drivers. So in this complex scenario, considering all these metrics, I think we have a very strong case for us to be Atmanirbhar in many ways. Now, in doing so, what are the gaps? Colleagues have mentioned about some of them. There are some of us who feel that on system engineering, if it is possible for somebody across the globe, it is possible for us. I would say in developing communication systems, a radar system, or in a sonar system in my area, I think if it is possible somewhere, it is possible for us. We know the fundamental limitations of the theoretical upper bounds, and then we know that systems can achieve almost close to the bounds, and there is absolutely no difficulty. But when it comes to some of the areas like technologies, there seem to be a gap. Particularly as Murthy was mentioning, precision mechanical engineering. Yes, we have a lack of precision technologies. And once we have lack of these precision technologies and the art of engineering and the art of technology is not mastered, we have these gaps. And when these gaps come, certainly in terms of resolutions on microscopes, in terms of things like the nano meter level junction uh, creation and associated processing, etc., growing layers and metallization, etc., would naturally come into picture. I think that's where we basically lack. Otherwise, either it in a software system development and are designing a supercomputer in the best possible way, or designing a communication system or a sonar uh, system, I think we do not fall short anywhere. However, so in terms of training our students, there is a gap. Not many of our students learn to do the system designs by the time they graduate, and that's where some of us are trying to do. So we need to somehow bridge the gap between, fill up the gaps existing in the precision engineering, particularly mechanical engineering, and make use of the strengths we have in system engineering. And that's what is the key. I think we can achieve Atmanirbharta in a number of areas. We can prioritize, certainly based on the implications on the economy front, implications on on our nation's uh, uh, priorities in terms of maintaining our sovereignty and independence on technology in some other areas. So this is what I thought I'll just share my views on Atmanirbharta and where we have a gap. Thank you.
Thank you, Professor Rajkumar, and I really appreciate for your kind words. I think we are waiting for Dr. Z.K. Dey. I think he's online. He just went somewhere, so let me just call him. So he will be there. He's just going to complete. He's going to complete. Hello. And just get Dr. Dey, please. So I think we are back. Dr. Dey is back again. So he was talking some important. Meanwhile, Professor Rajkumar conveyed his remarks, his ideas and opinions. So up to Professor Dr. Dey, again back to you.
Yeah, I'm sorry. These are the some of the disadvantages of video conferencing. You lose internet in between, and then you are gone without your wish. So I'll just take a couple of more minutes. I was talking about the transmission electron microscope, the first one of Asia. It was not made by the Japanese. It was made by an Indian in Kolkata, in Science Institute of Nuclear Physics, and then Das Gupta. He made a horizontal electron microscope, and this piece of historic relic is still there as a monument. If you happen to be visiting SINP, please go and see the only TEM of the country, indigenous TEM. But what has happened is, since then, that threat has been lost. We have not, followed it up with better microscopes. Had we done that, we would have been the best in making transmission electron microscopes. So we would have been Atmanirbhar in not only the use of microscope, but also in making the microscope. That unfortunately did not happen. But I'm very relieved, at least partly relieved, to see that SEMs are now being made. Our institute has made a SEM, which is good in capability, and it can do EDS as well. And they intend to make more models and make it available to the teaching institutions at a very reasonable price. So I hope that someday our country will become Atmanirbhar in making the microscopes also. We have shown, I just talked about how it has helped in us becoming Atmanirbhar in materials, but I hope that one day we'll also become Atmanirbhar in manufacturing the electron microscope. With these words, I would take leave. Thank you very much.
Thank you, Dr. Dey. Now we move on to Muralidharan, Dr. Muralidharan. Actually, I should say that, as some says, this function is also to honoring Dr. Murali. Dr. Murali?
Yes, Satyam, thank you. I'm just holding a cartoon of a Dasgupta microscope here. And I thank Dr. Dey for mentioning this. And I just want to talk and appeal to the current president, Avanish, that we should maybe commission a program in MSI to launch a transmission electron microscope of an Indian transmission electron microscope and maybe dedicate that to N.N. Dasgupta. That is a wish I want to make here, and I think all of us will work together to do that. And
I make note of it.
Yeah. So one thing I want to say that we had very large number of we had a large number of speakers. Yeah. We had a large, sorry for the disruption, large number of speakers talking about Atmanirbharta. I just want to talk about one thing. We have to see what have we learned over the years as our individually what we have learned, and we need to convert that knowledge to what you can give back to the community, what you can give back to Indian science. So one thing I've learned after working in DRDO and also later in CSIR, especially working in CSIR, is that the CSIR has got an I in it, which stands for the industrial research. Are we doing enough industrial research is one question I always ask. And I think the Atmanirbharta goes well with that. So if you all dedicate ourselves and contribute to that factor of industry and make whatever you make in the laboratory, if it can be made industrially and made useful for our countrymen, that's a job we have to do. I'm very certain that atomic energy, DRDO, space and all are already doing it. But can more and more people join this campaign and more of us can do this? And in what way we as electron microscopists can do this is one thing we need. And one particular thing we would like to say, I would like to say in this area is my 6-year-old niece recently talked to me in another function, and she told me she wants to be a scientist like me. So I said, what scientist? What kind of scientist would you like to become? And she said, I want to be a scientist and a virologist. See, the imagination has caught up with the young girl also. And that is the age we have to catch each and every one of them. And she wants to become a virologist, and she sees virology, she sees viruses. She says, I want to see viruses. And she said, viruses can be seen in microscope. You see, at 6-year-old, you already have the imagination of a virus, what a virus will look like, and there's a tool to see the virus. If such people can be driven, she's just an example, we will catch the imagination of the next generation, then next generation to follow. Then we will be making microscopes in this country. And along with that, if we train our youngsters with many of the programs, which many of us who are here in this meeting today, people heading Indian Institutes of Technology, people heading national laboratories, people heading many important institutions in this country. So if we work together, that is the Atmanirbharta we can do. And that is where we can contribute. And I think I will have more opportunity to speak to all of you in this very meeting. So I will stop here now, because in the interest of time, we should speak less, and we should speak more in other sessions. So that's all I want to say. I thank each and every one of you for listening and giving me this opportunity to speak to all of you. And thank you, Satyam. Thank you, everyone. Thanks a lot. Namaskar.
So I think, so I now go to Dipankar Banerjee to summarize and tell us this session, and also about Murali. This function, all function is to honor Murali. So this is up to Dipankar to say. Professor Dipankar Banerjee.
Professor Satyam, thank you, and good morning to all of you. I requested Professor Satyam that I should speak last because given the very distinguished people in this panel and the contributions they have made to Indian science and technology, I knew they would cover every aspect of what Atmanirbhar is about. And so I wouldn't have to say anything at all. And that is certainly the case. Srikumar provided this broad perspective of Atmanirbhar. Kamanyo emphasized the ecosystem from science to manufacturing and the necessity of filling all the interfaces in that ecosystem. And particularly pointed out the role of science in this ecosystem in providing a million solutions so that problems looking for solutions would have these solutions available to them. Professor Basu talked about Atmanirbhar in terms of mineral resources, and others such as B.S. Murthy, Alok, and Gautam, they talked about different aspects, computation, health sciences, artificial intelligence being important areas, the importance of instrumentation, design, and fabrication. Gautam touched upon the role of electron microscopy, and so on. And finally, Dr. Muralidharan, I think the key from his presentation was essentially the critical role of education in developing Atmanirbhar, and I think that's so important. I would have very little to add to this except to partially echo what Professor Rajakumar said, and that is, to my mind, to my personal mind, Atmanirbhar does not mean doing everything that everyone is doing in the world. And in a sense, this touches upon fashionable and non-fashionable that Srikumar referred to, but I would like to look at it in a slightly different perspective. I think we have a responsibility in our country, given its enormous geographic and economic diversity, its variety of strategic and commercial requirements, to critically, and I'm talking about technology and manufacturing now really, to critically define areas that we must focus on. And I believe that there are enough of these areas which are unique to our country, given proper planning and analysis, that we must address. And if we do that, I would believe that originality and Atmanirbhar will automatically follow. It's simply a consequence of appropriate problem definition, given the needs of this 2 billion population that we have with its diversity. So I think I'd like to conclude on that basis. We are right on time, Professor Satyam, and thank you very much, and I enjoyed listening to everyone. Thank you.
Thank you all the panelists, and I really appreciate all of you. I think before I conclude this one, it is my responsibility to thank the organizing institutes and the EMSI for giving us this chance. I think more importantly, the IMMT side, Dr. Ashutosh Rath, who actually behind us and is doing his and the computer team at IMMT is taking care of many of the things. So I really appreciate them and thank them, this young bunch of the guys who are really working hard. And I'm pretty sure the day ahead for us is really renowned speakers, very well trained and working for many decades. They are going to speak us on the special techniques in electron microscopy, and all the students are going to benefit. Certain small things also very important. This program of Atmanirbhar idea actually was given by Dr. Basu. He said that let's have a panel discussion. So I thank him for giving me that idea to have that one. And Professor Rajkumar suggested me, let's take all the students. So we declared, actually I should say that we declared a rescheduled IIT Bhubaneswar's classes so that they attend the meeting. This is important, and he felt from his own experience that the students should be part of this one. And I thank him for this idea as well, and thank all the students being with us and panelists spending their valuable time. And thank you all. And we all join at 12 o'clock, 15 minutes break from now. And first, I think last but least, Call Jace, would like to thank the Call Jace for financially supporting us to some extent. I didn't ask for money, but they said that if you need some money, we are there to help you. And thank you, Call Jace, with us. So we meet at 12 o'clock noon with Professor Kamana Chittapati as the chair, and the speakers are basically Professor Dipakar Banerjee and Dr. G.K. Dey. So this will be the speakers, and Dr. Kamana Chittapati will be the chairperson. Thank you, and have some good break at this time.
So let individuals have their tea. I'm sure it's a tea break, and individuals should take tea.
That's right. Thank you.
One tea.
We start at 12?
Yes, we start at 12. As per the program, we start at 12. So, thank you. Just a small break for you, and as I said, have a cup of tea in your own office. Thank you. The first technical session will be chaired by Professor Kamani Chitrapathi, who is teacher to many of the speakers here, I would say, and also very well known microscopist, material scientist, and many awards. I think it takes a lot of time to tell also those things. More than that is also our IFMC executive member. I request him to chair this session and introduce the speakers and take care of the session. Professor Kamani.
Thank you, Satyam. I hope I am audible.
Yes, please.
And let me introduce my good friend Dipankar Banerjee very briefly, because everybody knows him, but still there are a lot of students around. So I think it is appropriate that a brief introduction is given. Dipankar Banerjee is currently a professor at Indian Institute of Science and one of the leading material scientists, not only in India, but his reputation is across the world. He is one of the pioneers in developing some of the newer titanium alloys, some of which has now come into the aeroplanes. Some of the alloys that he has instrumental in developing has been the topic of discussions and being studied and now implemented in the aviation industry. His research publications are simply outstanding, and anybody going through Google or any other database will know that, so I should not talk about that. But what I should mention, particularly those students here, that he has not only done outstanding research, anybody who has worked with him, including me, we always get surprised by the depth and analytical approach that he takes, which is actually a revelation to work with him, the way he approaches a problem. But more importantly, that he's the only person, I think one of the few person, I should not say only, who also understand the industry, understand how things get implemented. I will not go in detail because most of the time he worked in defense, in a strategic sector, and not only he was a director of DMRL, Defense Material Research Laboratory, but he was also a chief controller, occupying one of the highest positions in the DRDO. And so, in that role, he has initiated and implemented many things that we are proud of. I'll just tell you one short, brief mention that what you see Tejas, the serial production of Tejas was done during his leadership. And I remember he was telling me, I have forgotten my research because day in and day out, I see whether this drop tank leaks or this fastener works. And that is what I am doing day in and day out for last 1 year. So you can see the perception he brings, rare perceptions of very high level research that will be very clear from his talk, but also very detailed understanding of how things goes from research to actual applications. With that brief introductions, I'll invite Dipankar to give his talk.
Kamanyo, thank you very much for that introduction. Thank you also, Professor Satyam, for inviting me to participate in this conference. I'm faced with some conflicting emotions here. It's not every day that a PhD student of yours retires. And it tells you something about your age. Kamanyo talked about the passage of time a little bit earlier.
And it certainly is telling you that it's probably time to stop speaking at these conferences. But this is one that I could not resist for a variety of reasons. First of all, it's a conference to honor Dr. Muralidharan. And of course, it's a topic that I have always enjoyed and loved dearly. So this combination of factors, it's a wonderful opportunity to be here and speak to you all. So I will start sharing my slides, and you have to let me know whether you are seeing this. Is it visible?
Yes.
Yes.
Okay, good. Right. So Dr. Muralidharan joined us from Banaras Hindu University and then Midhani. And you see him in this picture here in the center, which I have encircled. And this was taken on the occasion of a holy day. And you see him with a bunch of people, many of them from Banaras Hindu University, whom I have always enjoyed working with. He joined us as a very impetuous young man, but full of enthusiasm and a boundless capacity for very hard work. His contributions, and certainly through his PhD program, and then subsequently in DMRL and DRDO, and then CGCRI, had been enormous. He now has retired as director CGCRI, and that also brings to a close a very long professional association that I've had over so many years, and that continued to the day that he retired, because I was chairing the CGCRI Research Council. I'm sure others will talk about what he has done in this period, and I will only say what enormous pride I take in his achievements and his contributions to our various areas of research, and in particular, which wants to reach out. Have I gone off screen?
Looks like we're missing.
Yeah, you're back, I think.
Yes, yes. Can you see the again? Is it visible?
No, you can probably have to share.
You don't see the screen?
No.
No.
Okay.
So you close the sharing and again start the sharing.
Okay. Now?
Yes.
Yeah. Yes.
So this is going to happen. I mean, some interruption in signal. I'm sorry about that. So what I want to do today in this talk is, given the scope of this conference and that it's addressing a wide variety of students, particularly, is to sort of integrate some of Murali's contributions to this area with a broad overview of what electron microscopy can do for materials engineering. So historically, in a sense, electron microscopy really grew out of several important advancements. There was de Broglie, who talked about the theory of the wave nature of electrons. There was Hermann Busch, a very important engineering contribution on axial magnetic fields and how they refract electrons. And so electron optics was born. And then it also led to a Nobel Prize for Max Knoll and Ruska in 1986 for their contributions to this field. Much of what we do in electron microscopy today depends on the interaction of electrons with the specimen. And amongst these very wide variety of interactions, and many techniques will be covered at this workshop, I will focus essentially on transmission electron microscopy. And so we're going to talk about transmitted electrons, the transmitted beam, which goes through without any deviation. We're talking about coherent elastic scattering by an outermost electron cloud, which provides the diffracted electrons. And then we're going to talk about elastically scattered electrons, which allows high-angle annular dark field imaging, and inelastically scattered electrons and its relationship with electron energy loss spectroscopy. The accelerating voltages that we look at in transmission electron microscopy range from today from 200 kV to 300 kV in most cases. The imaging system itself provides, first of all, the microscope provides, first of all, the electron source, which could be a tungsten filament, a Lab6 filament, or a field emission source. And then the imaging system collimates this electron beam, this accelerated electron beam, onto the sample. And then a couple of things occur that we are interested in. One is the transmitted electron beam and the diffracted electron beam. And the subsequent imaging system can either pick up the diffraction plane, that is where electrons moving in the same direction come into focus, or the image plane, which picks up in focus electrons coming from the same position in the sample. And then there are various detectors. So there are X-ray detectors, there are electron energy loss detectors, there could be other detectors and so on. And then you see an example of diffraction patterns that we get when we pick up the diffraction plane in the system. So you have, if you have a system of parallel beams, then you have the diffraction pattern that you see on top. If you have a convergent beam, then you have a different kind of diffraction pattern that's called a convergent beam diffraction pattern. And in a combination of these two, you can derive, at the spatial resolution that the TEM offers, you can derive point groups, space groups, and so on. Sample preparation is an important part of transmission electron microscopy. Given the energy of the incident electrons, they have to be transparent in transmission electron microscopy to the electron beam. And so your sample thicknesses can be usually no larger than 1000 angstroms, should be very often as low as a few angstroms for some of the work in aberration corrected microscopy that people are doing today. There are various ways of thinning samples. They could be electropolishing, ion milling, ultramicrotomy for biological samples. But of late, what has come into importance is the focused ion beam method, together with the dual beam electron optical equipment, which allows you to thin samples in a site-specific way. And that's, of course, extremely important for correlative microscopy. In its basic form, TEM relies on diffraction contrast. So you can do phase identification distribution by putting a physical aperture on the transmitted beam or any one of the diffracted beams, and you can identify which phase has which crystal structure and so on, and the distribution of phases. You can use strain fields in the sample associated with defects which affect local diffraction to image defects such as dislocations, or the displacement associated with planar defects such as stacking faults to image these defects or faults in terms of the very characteristic fringe contrast. With that background to basic electron microscopy, I'm going to provide you with a few engineering examples of the application of electron microscopy in material science. We've talked a lot about Atmanirbhar this morning, and it sort of expands on that theme, if you will. So here's an example of work on titanium alloys, primarily carried out at the Defense Metallurgical Research Lab, and addresses the issue of high temperature capability of titanium alloys. The upper limit of this capability is defined by the oxidation resistance and the burn resistance of titanium alloys. And if you want to increase temperature capability, you have to look at the intermetallics in the titanium alloy system. So there's Ti3Al, there's TiAl, and there's Ti2AlNb, as shown in this phase diagram. And work at Defense Metallurgical Research Laboratory focused primarily on the intermetallic Ti2AlNb. Through the 80s and 90s, we defined the entire physical metallurgy of the system in relation to and product development. And Murli, as I'll call him from now on, contributed much to this effort, very specifically through his PhD program in the field of phase equilibria and transformations in the system. So his work critically and classically defined the phase diagram in the system. Through convergent beam electron diffraction, he was able to identify two forms of the Ti2AlNb phase, two different ordered forms. And you can see the kinematic intensity differences associated with these two different ordered forms. And in this conjunction between transformations and equilibria, he defined phase equilibria in a way that could be used in engineering the system to the properties that we wanted it to have. He looked at the variety of transformations that occurred in the system. And here is an example of his work showing the transformation of Ti3Al to Ti2AlNb that occurs if you look at that phase diagram on the right-hand corner here. And what it shows you is the very complex but very unique microstructures that evolve as a consequence of this transformation. Analyzing these microstructures involved understanding the complexity of this diffraction pattern, the variant distribution associated with this diffraction pattern of the Ti2AlNb phase that forms as these plates in the matrix. It allowed the analysis of groups of variants that formed experimentally, and it involved the analysis of the shape strain associated with each of these variants and how grouping of these variants could minimize the overall elastic energy of the system. Murli also looked at the transformation from the parent BCC phase to the ordered Ti2AlNb phase. And this involved a slightly different kind of microscopy. It involved the microscopy that I alluded to earlier of looking at the interaction between the diffracted beam and the defects in the system, the coupling of the diffraction vector and the contrast that you get in the microstructure as a consequence of the defects existing in the system. And so he was able to define in the course of this transformation the various different kinds of faults that occurred, various antiphase boundaries, for example, as shown in these images of contrast with different diffracting vectors. And he was able to completely define the mechanisms of this transformation that allowed us to control the microstructure in a way that we wanted for mechanical properties. I'm going to shift this engineering emphasis now to another area, and that is in the area of electronic devices. Defense requires high power, high frequency devices. And gallium arsenide, gallium nitride and silicon carbide form the core of such devices, which are used at high temperatures with high power and high frequency. In contrast to the use of silicon in other devices. And so such devices form monolithic microwave integrated circuits, MMICs, that are used for microwave mixing, power amplification, low noise amplification, and high frequency switching in a variety of military applications. I want to show you the scale of these MMICs in relation to your thumb, and below there, a transmission electron micrograph of one of the MMIC, one of the devices in this entire MMIC, and the scale of that device. What do we want in such a device processing technology? We want measurable go, no-go properties at every stage of the process and not just the device as a whole. And we want the material science that underlies these properties. And so we want to derive a relationship between structure, cost, processing, and device physics, architecture, and function. And we did this in collaborative programs between DMRL, IISc, DMRL and SPL initially, and GATEC, and then IISc and SENSE. I want to again focus you on the scales of these devices. And again, you can look at this micron marker here and show you the device as a whole prepared by transmission electron microscopy techniques. And the relationship of the scale to the scale of the influenza virus, for example, just so that we have a connection to life sciences. What Murli and his colleagues at DMRL, Sridhar Rao and Saha, who are both here as well, I believe, did was to actually develop the entire set of electron microscopy techniques, everything that goes with the electron microscopy of such devices, and that characterization at various length scales, ranging from microns to nanometers to a few angstroms. And this contribution, and I think it's no exaggeration to state that this contribution put India on the map of electron microscopy of electronic materials. There was no work in this area prior to that, and the contributions this electron microscopy capability has made to device development at SPL and at IISc is quite enormous. And so here is the leadership role that he and his colleagues at DMRL really took forward in ways that are quite remarkable. And so look at the length scales here and the capability of site-specific characterization. We can look at the gate. We can look at the interface between the gate, the source, and the active layer of the device. And so we can understand and characterize structure, defects, composition at every one of these length scales, including that nanometric length scale of the active layer over there. So here's the length scale of that active layer. And you can see that it ranges from a few nanometers in these active layers to something like 50 nanometers or even 500 nanometers. And what we have to do in understanding the material science of such devices is to understand the composition of the individual layers, because they are engineered to allow band offsets, which allow modulation doping. We have to understand the heteroepitaxial strain of these interfaces in these channels, because they affect device performance, and therefore the knowledge of both composition and strain in these epilayers are very important in device, in the understanding of this device technology. And so we have two new techniques that I now have to talk about, or three as we go along. So one is phase contrast. And I talked earlier about putting your objective aperture around the transmitted beam or the diffracted beam. But if you put your objective aperture around the combination of transmitted and diffracted beams, then you get phase contrast in the microscope, and the interference patterns that you get represent the position of the atoms in the microscope if you do it correctly. And I'm sure people are going to talk about this in more detail later, but you can see an example of atomic resolution using such a technique with these defects that you see, dislocations over here. A second technique is to use high-angle annular dark field imaging. And what this does is to use elastic scattering by the innermost electron crowd and image that elastic scattering process through higher angles. Something like 10 millirads is the limit of Bragg scattered electrons. You're looking at high angle scattered electrons to the extent of something greater than 10 millirads. If you then make your probe, and you can do this in two ways. You can your probe size can be varied in modern aberration corrected microscopes, and there are going to be talks about that. But if you make your probes about or smaller than the interatomic distances, then you can image the scattering centers. That is, you can image these atoms because the atoms are the scattering centers. So you can get atomic resolution by scanning the probe over the sample such that you can image the scattering centers at different positions in the sample with atomic resolution. So here are examples of work that Murli and his colleagues did out of DMRL. and I'm going to show you some slightly different aspects of this work. So this is high resolution electron microscopy of the gallium arsenide, indium gallium arsenide, and aluminum gallium arsenide structure. And the technology problem is to control this composition here such that you get the kind of band gap that you want. And you have to control the composition and therefore the strain in the material. How do we measure strain at these localized situations? Well, one technique is to look at these high resolution micrographs, look at the positions of the atoms or the interference patterns that lead to the atom positions, compare it to the positions of the atoms at some base through very careful digital analysis of these high resolution transmission electron micrographs. You can then define the displacement of atoms in this indium gallium arsenide layer in this example in relation to the atomic positions in the gallium arsenide. And because you can identify the displacement in these layers, you can then arrive at the strain in these layers as a function of the original lattice parameter of the unconstrained indium gallium arsenide. This must be accompanied by a knowledge of composition, because you have to relate composition with the strain. And so Murli and his colleagues, Sridhar Rao and others, achieved this by developing quantitative high-angle annular dark field techniques. It's easy to get qualitative data on composition from high-angle annular dark field because the scattering process is dependent on the atomic weight of the atoms that scatter these atoms. So the contrast that you get in HRDF is dependent on composition, but you have to quantify it, and quantification is not a simple matter. You have to do a variety of calibrations of the imaging system. You have to do simulations of the scattering process, and you have the experimental data and intensities, and you combine all of this to get at a quantitative map of composition in these samples. This is HRDF at less than an atomic resolution. It just shows you the layers in the structure and the composition of these layers, but does not show you composition with atomic resolution. I'm going to show you examples of that a little bit later. But here's another example of critical device technology work and TEM supported device technology work that was done in collaboration between DMRL and the Indian Institute of Science now. And these devices were being processed at the Center for Nanoscience and Technology with Professor Raghavan at IISc. Krishna and Krishna was a PhD student with me in IISc. Saha was Murli's and my PhD student out of DMRL, and we looked at the microstructure at every step of this process at these length scales to define the effect of processing parameters on the quality of the layers that were grown. So here is an example of high resolution electron microscopy, and it shows the structure of the nitrided layer, the very thin nitrided layer that exists between the sapphire substrate and the gallium nitride. And the structure of this nitrided layer had not really been known before. And look at the thickness of this nitrided layer. It's actually less than 1 unit cell of the aluminum nitride, which forms this nitrided layer. And we were able to understand the mechanisms and the effects of processing temperature on the structure of this nitride layer and its importance in the quality of the gallium nitride that sits on top of that. I now want to conclude, and these are my last few slides, on another technique which complements transmission electron microscopy. And this is atom probe tomography. And the idea is that you can emit atoms from a very sharp tip through the application of a field or laser pulsing. You can analyze the time of flight of those atoms, and you can relate the composition of those atoms to the position in this sharp tip. And therefore, you have the potential of looking at the three-dimensional structure with chemistry information. Okay. So I'm now going to show you examples of work, and this is work that we've been doing very recently at IISc and really represents the state of art in electron microscopy in this area. And this is work out of Kamanya's group, work on cobalt alloys, work by his former PhD student, Surindra, who is now a faculty member in ISC and uses the atom probe tomography capability in ISC, and Abhishek Sharma, a PhD student who did the CREEP. And what this work did was to define CREEP properties of these alloys. And so you see a comparison of stress temperature and the microscopic mechanisms that are associated with creep of these materials. So you have, for example, a situation where dislocations are just confined to these gamma channels of this two-phase FCC matrix and Ni3Al precipitate structure. So a stress temperature combination in which dislocations are combined to these, restricted to these channels. A stress temperature composition at higher stresses in which the Ni3Al is sheared. And I want to talk to you about some examples of the shearing process to illustrate the power of combining TEM with atom probe tomography. So here is an example of now atomic resolution, high angle annular dark field microscopy. So this high resolution work with HRDF is high resolution of these twins that result in this structure when Ni3Al is sheared at this low temperature, high stress regime. And what the HRDF immediately tells you is that there is a composition segregation in these twins. So energy dispersive, and you can look at the intensity difference here between the twin and the matrix. A higher resolution picture of these interfaces also tells you that there is additional segregation at the twin matrix boundary interfaces. However, it is very difficult to quantify energy dispersive spectroscopy, and later talks will probably look at that in more detail. So we combine this work with atom probe tomography, and you can see here, and this is the gamma phase, that is the matrix. This is the gamma prime phase over here, that is this phase over here, and this is the twin boundary within the gamma prime phase, that is this region of the TEM microstructure. And when you do that, you can see the segregation of cobalt, molybdenum, tantalum, and nickel to the twin boundaries. Okay. A second example is at higher temperatures and high stresses. And at these combinations of stress and temperature, you again have shearing of the Ni3Al, but now instead of twinning, the shearing results in the formation of anti-phase domain boundaries. And it is extremely difficult to look at segregation at these faults because the faults are curved through TEM, because TEM always provides you with a projected structure. And so here's an example again of atom probe tomography. So this entire area here covers in atom probe tomography this area over here. This antiphase boundary is imaged over here in atom probe tomography. This is the matrix over here, and this is Ni3Al. And again, you can see the segregation quantitatively of various alloying elements in this alloy to these faults. So what we have is a situation that we could not imagine even 5 years back, but which has evolved with this combination of HRDF and atom probe tomography to image Suzuki and Kotzl segregation during the shearing process under creep in these structures. And essentially such segregation we now understand controls dislocation dynamics. And let me emphasize again, this could not have been understood or even characterized without this complementarity of TEM and atom probe tomography techniques. And so the question in terms of engineering is that this really leads to a new alloy design philosophy. Earlier alloy design philosophies focused on just the size, the misfit, the volume fraction of these precipitates. And now we have to worry about segregation and segregation-driven dislocation dynamics which control plasticity in these materials. So I'm now going to, let me show you that atom probe tomography is also a three-dimensional exercise. So on the right, you have a video which allows you to, which shows you that you can look at this atom probe image in 3 dimensions, unlike most TM. So let me conclude then, and really conclude by saying that transmission electron microscopy occurs at very different length scales. You can look in basic electron microscopy at the submicroscopic or nanometric length scale. With increasing capability as the instrument has evolved, we can do image resolution to sub-angstrom resolutions. We can do atomic strain mapping. We can do chemistry with subatomic resolutions. We can combine that with atom probe tomography, an area that I have not touched upon in this talk, but just to point out that electron energy loss spectroscopy combined with the focused probe that is available with today's instrumentation allows you spatial resolution defined, angstrom spatial resolution defined, band gap measurement, dielectric constants, surface plasmon loss, and a variety of valence states. All of this requires something that Kamanyo touched upon. Okay, it's hard work, but the pleasure of the universe that is revealed makes it worth it. And I must emphasize what Sri Kumar pointed out, that the combination of these techniques with techniques that are used at different length scales, such as synchrotron diffraction, for example, leads us much better to a total understanding of the system. Thank you very much.
Thank you, Dipankar. Shall we invite some questions, Satyam?
One or two questions, yes, sir.
If something is very
that's right.
important,
We have also asked the people to type on YouTube as well. There is actually there is a lag from YouTube to this conventional one. So in the Microsoft to YouTube, there is a lag, maybe about a 1 minute lag. So we leave 1 or 2 minutes. Those who have to ask questions, maybe they can ask questions. I mean, that's my suggestion. It's up to you, sir. It is.
No, this lag creates difficulties. So I think it is better that to keep the audience interest intact. I think if people who are there already in the here, if they ask anything to be asked briefly.
I have, if you allow me, I have some small queries, sir.
Sure.
So, Professor Dipankar is a wonderful talk actually, and also giving a basic ideas about electron microscopy with various levels. I just have a small query. This quantitative STEM analysis, one of the biggest problem what I understand is thickness, knowing exact thickness of the specimen.
Right.
So how are you actually handling this problem?
Well, the thickness measurement was part of the computation capability that was available by someone that you worked with, Andreas Rosenar. Okay.
Yeah.
And essentially, the intensity is you compute the scattering that in HARDF, and you relate the scattering to the intensity that you get, and therefore arrive at the thickness. That is one method. There are other methods. One of them is thickness determination by convergent beam electron diffraction. Murli has done so much, and he did one of the first methods of thickness determination by seabed as part of his PhD thesis. I didn't talk about that. The other method is using electron energy loss spectroscopy, because the zero loss peak intensity is proportional to thickness. So there are a variety of methods by which you can get thickness. And you're absolutely right, Satyam. Thickness determination is a key to all computational work, which relates the image that you see and the diffraction that you see in order to be able to interpret computationally. And you also pointed out a very important issue that was indirectly reflected. You cannot today in modern microscopy do microscopy without computation if you want to quantitatively interpret images. You can get away by qualitative work, and that's important as well. But if you really want to do cutting-edge microscopy and interpret images quantitatively, you must be able to combine simulation with computation with your experimental work. Yeah.
Thank you.
Ashutosh?
Hello, sir.
Hi, how are you?
Back. Yeah, good. Sir, I have a very one questions on this indium gallium nitride supersonic structures. So there is, when you study these grain boundaries, twin boundaries, so there is a method, it's called, you can do the electron analysis in the spectrometry on the grain boundary, where you can find whether you can find out like what is the difference between the grain boundary, on the grain boundary, and off the grain boundary.
Yeah.
Atomistically.
Yeah.
Using the atomic electron spectroscopy, and for that, the thickness measurement you have to do locally using your zero loss peak using electron loss yields.
Yes.
Yeah.
So in that way, if you can find out what is the how the atomic position each atom has in the grain boundary, then you can get more information by doing the same simulation as you mentioned. So that's just my comment on it. So you can do each atom on the grain boundary and what is the grain boundary and the off grain boundary interface. That may give you more information atomistically, or science point of view can explain more on it rather than. So that is just my comments on it. Yeah.
Ashutosh, that was a very important comment, and perhaps I didn't emphasize this at all in my talk. But interfaces control material science and engineering in the nanometric structures and in micron scale structures. Interfaces are extremely important. And therefore, whether it be grain boundaries or phase interfaces or whatever, and the ability of the modern aberration corrected microscope to provide probe sizes of the order of the atomic size allows us, as you say, not only to define atomic structure in chemistry, but also to look at valence states across interfaces.
Exactly.
To look at phonon dispersion across interfaces. It's amazing what you can do today with electron energy loss spectroscopy. Yeah.
Exactly. So with that one, if you incorporate the STEM simulation, which basically accommodate your phonon contributions, then you can compare your exact atomic positions, each atoms with the experimental results. Then you can get most science out of it.
The importance of looking at valence band structures, phonon dispersion, plasmonics, and so on, depends on the resolution capability of your energy loss spectroscopy, and therefore you have to separate the plasmon peaks from the zero loss peaks, and that requires both a control over wavelength of the electron beam to very accurate values, as well as the electron energy loss system, which allows the the energy resolution. Yeah, that's a very important component. And conventional electron energy loss spectroscopy will not allow you to deconvolute the zero loss peak from the plasmon loss peaks that are important in phonon dispersion studies. I also didn't emphasize in terms of techniques, and maybe someone else will, but the imaging system today has gone from film to CCD to CMOS, but very importantly has gone to direct electron detection. These are extremely important because they allow for very high frame rate capture of the images, especially the direct electron detection techniques. They're extremely expensive, but represent the cutting edge of the field in imaging what is going on. Yeah.
Thank you.
So, Sir Kamanyo, there is a question from an audience. Shall I read it out?
Yes.
So there is a question from, two questions are there. One is Radha Krishna Das. Is it possible to get a dynamic image of the physical and chemical changes in real time with electron microscopy?
In situ electron microscopy is again something that I did not touch upon, but you can today incorporate cells with certainly temperature, strain, and even reactions in special stages in the transmission electron microscope. So you can evaluate reactivity at the nanoscale. You can look at temperature effects on structure. You can look at stress effects and strain effects on the evolution of defects. So the answer is yes.
Okay, I think we lost
We lost
Dipankar.
Yes, I think we should go ahead.
Just wait a few minutes whether he gets back. Well, if not, then I think we thank him.
Yes.
And we can mail our thanks to him and move on to the talk by Dipankar Gautam De. Gautam, you're there?
Dr. De, he was there. I just talked to him some time back. So let me ping him. Let him ping him. Yes. Dr. De. Don't see him. So let me call him. He's just. So these are all expected.
Dipankar is joining. Dr. Banerjee is joining back. So,
Power failure and a generator takeover.
Right.
So
right.
sorry about that. Fortunately, there's a generator backup.
Okay, okay. Yes. So, Dipankar, I think, thank you very much for your very exciting talk. There are many questions. Even I have a questions in my mind. But I think if Gautam is delayed, then I'll ask the question.
Yeah, I think you go ahead. Gautam seems to be on another call.
You can go ahead.
Let me see.
Gautam is on another call. So
What Abhishek is on which, and that segregations in the TM as well as what Surendra has done is very interesting. But my question is, okay, we know a particular kind of segregation is taking place when there's interactions and when there's a cutting. From there, you mentioned that this can give a clue for developing a better alloy. How we should go about doing it? Obviously, we have to decide on which one of the segregations at that dislocations, Suzuki or whatever may be, are more effective and therefore strengthen and add those compared to other alloying elements. Am I right?
There are two aspects. Well, there are three aspects to this, Kamanyo. One is that you want the segregation because it stabilizes the fault and therefore minimizes the deformation process thermodynamically. The second important aspect, and that is what you alluded to, the second aspect is the kinetics of the process. Ultimately, the motion of the dislocation, the partial with its scattral atmosphere and the fault behind it, is controlled by the diffusivity of the species. And so the relevant activation energy for diffusion, whether it be bulk or pipe diffusion or whatever, is something that you would like to control. Okay, so there's the thermodynamics, there's the kinetics. The third part is where we all struggle with, and that is the role of alloying addition is not just on these factors, but it also affects oxidation, volume fraction, misfit, temperature stability, and so on. And it seems almost impossible today to build up computational techniques which will address all of this simultaneously. And therefore, I think the importance of artificial intelligence in aiding computation, which addresses all these issues simultaneously. I hope that was a comprehensive enough answer.
Yeah. You see, I always look at it as what I can do next. That was the question. That was the spirit behind the question.
Sure.
Okay, I think Gautam is in.
By the way, Kamanyo, the application of AI and computational techniques is quite well established in ISC, and so it's easily possible to look at this as a subset of the work that you're doing in parallel with whatever you do with intuition.
Yes.
I think it will help you in
I told my students to collect all the data that we have done last 5-6 years, and then maybe you, Abhishek, myself, we'll sit down and Surinder and see what we can do.
It needs a combination of people who are familiar with the metallurgy, with the material science, and a combination of the computational capability.
Last week only, I sent them a paper of AI and told them to collect all the data that we have for last 6 years.
Right. Okay, thank you.
Gautam, you are in? Gautam?
Yeah, I'm again admitting it. I'm admitting him.
I have admitted.
Okay. Then Dr. Dey, are you in?
Yeah, I think I'm in. I'm trying to share my screen actually.
Okay. Okay. Before you share your screen, let me introduce you.
Yeah.
So, Professor Dey is Raja Ramanna Professor, distinguished fellow at SBNI, Homi Bhabha University, and he's also I think you are the Dean of SBNI, right?
No, I was Dean, and actually I'm associated with PRC and not HBNI. I continue to be a senior professor in HBNI. Yeah.
Okay. And he graduated from, again, Benares Hindu University and did PhD also from Benares Hindu University with Professor Ramchandra Rao as one of the supervisors. And he's actually associated with electron microscopy lifelong. And Shikumar Banerjee and Gautam Dey are part of the development of microscopy that has taken place in this country. And he, in fact, the first Titan microscope, he is instrumental in setting up the first Titan microscope in the country and working with it. He has also worked with the different techniques of microscopy, and not the classical ones like me, but extended it into many different things. And that is something what he is going to talk today, fluctuation microscopy, where he has done enormous work and his contributions are praiseworthy across the world. So without any further ado, let me invite Gautam Dey to give his talk.
Thank you, Professor KC, for the kind introduction. And I also want to thank Professor Satyam for inviting me to give the talk here. It's always a pleasure to talk in a forum like this. The title of my today's talk is Study of Structurally Disordered Solids by Transmission Electron Microscopy. Now, we will be hearing a lot of talks in this conference, and I don't know how many will be on materials which are not crystalline, but if you look around us, you will see that very few materials around us are actually crystalline or quasi-crystalline. Most of the materials around us fall into a different category where the atomic arrangement is not periodic. However, these have not been investigated in the kind of detail that they should have been. So this talk essentially tries to focus on examining such solids which will broadly fall into the category of structurally disordered solids. So this is the outline of my talk. The first section talks about the challenges and motivations for studying structurally disordered solids. As I just said, these have not been studied. And the reason is there are many challenges in examining these structures because the atomic arrangement is neither crystalline nor quasi-crystalline. Okay. So the first part talks about those challenges and what will be the motivation for doing such studies. And in the second section, we look at how to overcome those challenges. Particularly, since this is an electron microscopy meet, I will talk about electron microscope as the tool for overcoming those challenges. And finally, I conclude. So when I say structurally disordered solids, I mean solids which lack long-range order, both translational as well as rotational. But
can you go to slideshow mode? You're not in slideshow mode.
How is that?
It's okay, we can see
I
it.
can see it.
Okay,
No. But I have to go to slideshow mode.
Yeah, please go to
Are you able
the slide. No.
Why is that?
Continue, please continue. Yeah.
No.
Gautam, you go to the slideshow.
Yeah.
In your screen. Well,
I have actually on my screen. I'm in the slideshow mode.
Okay, again reshare.
Yeah, you to reshare. You to
Gautam, you get into slideshow mode in your screen and then share.
right.
Has it come?
No, nothing is visible now. So first you have to share, put it in the screen. Screen share should be done last.
How about this? What do you see? Do you see?
No.
Now we see this. Now you do a slide. In your screen, you do a presentation mode.
Full screen. No, that's what I'm doing. I can see it's full screen, but you are not able to see. That's the problem.
Anyway, you go ahead the way you were. It's okay.
Yeah.
No. What do you see now? Do you see anything?
No.
You don't see anything. How is that?
We just see G. On the Facebook, we are seeing the slides. No. YouTube, you are just seeing the, not the slideshow again. Just your slides are being shown. Let's try. Yeah, very nice. It's good now.
No.
Yes. Yeah.
Good.
Do you see?
Yes.
Carry on. Yeah, carry on. Very nice.
Will this do?
Yeah, this will do. This is correct.
Okay, fine. Sorry for the interruption. So as I said, the structurally disordered solids are solids which lack long-range atomic periodicity. So the order is neither translational nor rotational, but you have very well-defined short-range order. So that is the characteristic of structurally disordered solids. And not only you have short-range order, that is SRO, you also have medium-range order. Okay, so medium-range order may not be that well-defined, but it's very much there. And since the atomic arrangement, as you can see in this adjoining picture, it's not well packed, therefore you will have voids. So there are three components to it: short range order, medium range order, and voids. So there's a large number of materials falling into this category. Just to name a few, nanoparticles, top layers of many coatings, grain boundaries, and many ceramics, because the ceramics have a very wide boundary, and that boundary, the atomic arrangement is not crystalline or quasi-crystalline. It is what is structurally disordered. Then you have glasses, both the categories, metallic and non-metallic. You have amorphous silicon. You also have metallic clusters. All these fall into the category of structurally disordered solids. This list is actually much bigger, and what I have put is not exhaustive. Then yeah, so what is the for this particular presentation, out of all this, I have chosen the glasses as an illustrative case, specifically the metallic glasses. And what will be the motivation for studying glasses, that is metallic glasses specifically, is given in this view graph. The metallic glasses have a lot of synergy with the other form of glasses, that is the silicate glasses, which are of course much more voluminous in use and applications of various types. So if you understand the structure of the silicate glasses better, much better than what it is right now, we will be able to engineer glasses for specific applications. The second motivation is these glasses also have defects, but since we don't know the structure itself fully well, we don't know what the defect nature is, because the defect is a deviation from the particular structure. So this kind of study where you are deciphering the structure in detail will help us in understanding the defects in detail. Then for us in the nuclear industry, we use glasses of various types, and radiation does affect these glasses in a big way. But if the structure of the glass before irradiating is not known, you will not know what are the subtle changes being brought about by radiation in these glasses. So there again, the structure of glasses should be known in as much detail as possible, and these studies can help. And last but not the least, here is an example where this kind of study can also help in understanding solidification better. What I have shown is a schematic where you have crystals and you had liquid. You had liquid before, but since you froze it quickly, that liquid has turned into glass. Now, it's very difficult, almost impossible to study the liquid, but it's possible to study the glass. Therefore, I would like to know how the liquid was just before it turned into crystal, that is at the interface on the liquid side. I cannot study the liquid, but I can freeze that and study it in form of glass. So this kind of study will also reveal a lot about solidification, and I'll give you an example of that towards the end of my talk. So that with that preamble, now I come to the techniques involved in studying these aspects. I come back to the components of the structure of structure of a structurally disordered solid. As I said, it has three components: the short range order, the medium range order, and the voids. Unlike in a crystalline material where you have a motif which gets repeated, so you can use a single tool like a transmission electron microscope in the imaging and the diffraction mode and study almost everything. But here you cannot use a single tool or a single technique in the TEM for understanding all three, that is short range order, medium range order, and voids. Therefore, we have used a combination of techniques to understand each of these aspects, because without understanding the full range of aspects, you cannot talk about the structure as a whole. So for instance, we have used three global tools, that is, these tools give information from the entire specimen, namely XAPS, SACS, and positron annihilation. XAPS for SRO, SACS for SRO and MRO, and positron annihilation for understanding what are the open volume or the pores present in the structure. We have also used four local tools, namely the 3D APFIM, which gives us information about SRO and MRO. Then we have used a new form of transmission electron microscopy, which is known as the fluctuation microscopy. Also, we have used a specialized form of filtered high resolution electron microscopy, which will give information about the open space, that is the free volume or the voids inside the structure. And finally, we have used the angstrom beam electron diffraction for understanding the nature of the SRO and the MRO present in these structures. Since this is a since it's an electron microscopy conference, I will not talk about all these tools. I'll just talk about the last three, which are based on transmission electron microscopy, the new forms of electron microscopy. These are new techniques which have developed in the past decades, and some of them have been developed in about the last 15 years. I'm very fortunate to be in an institute like BRC where it was possible to do all these studies, because a single person cannot do all these studies, and therefore you saw the names of my colleagues who have participated in these studies. Their contribution is no less than mine. So I will, as I told you, I'll concentrate on the last three. To begin with, we need to know what is the short range order. So I will talk about a technique based on short range order determination, and this is the angstrom beam electron diffraction. So here actually you use a beam which is 0.4 nanometer, that is 3 to 4 angstrom in size. Such a small beam can be generated in a modern corrected microscope, more specifically a probe corrected microscope in the scanning mode, and we have several such microscopes across the country.
Are you moving the slides?
Yes.
It's not moving. So we got stuck at the motivation slide.
Oh my God, why is that? Where are we now?
Motivation.
Getting motivated.
Where now? Probing the structure of glass?
No.
We are still stuck in motivation only?
Yeah,
Yes.
we are keeping motivated ourselves.
No, I think, Professor Satyam, I am wasting time of others.
No, you go back and reshare. Whatever comes, you go.
Oh, very bad.
You get out and again share.
Yeah, you said correctly. I should get out from here.
Dr. Day.
Yeah.
Are you sharing the slide or you're sharing the screen? That is, if you're sharing the desktop, sometimes it freezes.
I think he's sharing the desktop.
Share key. What do you want me to share? Tell me.
Presentation.
Share the slide.
Share PPT. Possible.
No, you do the share first. Then the screen will come and this particular folder will come, You do a share it, then it will ask you share from where?
Then share PPT.
Okay, then where is your slide? You just click that.
What do you see now?
It's just
yeah, we are seeing your computer. That you go to the slide.
No, I have gone to the slide.
I think there's
No, you are not in the slide. You have to go. You are seeing all your desktop.
Sir, we can close the video of yours so that we can increase the bandwidth. Your video can be closed, sir. Better there.
Closed.
Okay, now let's see. Just click that one, yes. So other option is you can send me an email, I will share it.
No, you share your
Share PowerPoint.
No, there's nothing like a shared PowerPoint. You do a share content. You click that. then it will give you two options. No. You go to your, you unshare your presentation. Unshare your presentation and then
it says Microsoft
share
Teams.
it again.
It says screen F1, screen 1.
And then it gives option. What are the options you are getting?
I am getting quite a few options. I am getting screen 1, Microsoft Team, join conversation, Google, Microsoft Point, expansion drive F.
No. None of them should be. Okay.
Sir, you can
Share
send me an
screen
email.
you do.
Sir, you can
You
try
do share
otherwise.
screen.
Pardon?
You do the share screen.
Near to the mic. You know, right? Setting.
How was it working in the beginning? I didn't understand.
Yeah, now we are back.
No,
So let it be in this mode only, sir. Go to the slide.
The second slide. Is it the second slide?
Now it is second. Now outline.
No, we are in the outline. Go forward.
Go forward, sir.
Yeah.
This is further. Go next. This is viewer here. So you go to the next one. Yes, I think from here onwards we did not see.
Are you seeing
now?
the next
Now
one?
it is angstrom beam.
Pardon?
Angstrom beam. Yeah.
Yeah. Are you seeing this principle of ABED?
Yes, we are seeing that.
I am terribly sorry for this mix-up. You know, I don't know how to apologize. I don't know why.
The best way is not to. There's no need of that. It's the internet problem, sir. Don't worry. Please go ahead, sir.
Okay. See, so this is a new technique developed in Japan by a group of scientists. Akihaka was the leader. And here what we do is make the beam small, 3 to 4 angstrom, and try to get diffraction. One would wonder whether you can get diffraction from such a small beam, even if you have small clusters. And therefore, there's a need to discuss a little bit about the principle of ABED. The equation here shows the diffracted, the intensity of the diffracted beam from a small cluster where you have two atoms, one located at position N and the other located at position M. So there is a vector joining them, and you also have the scattering vector Q, and then the FQ is the electron scattering factor. So when you have this, then you can have a diffracted beam from a regular structure, even with two atoms, but not in a gas. In gas also you have atoms, but they do not diffract the same way as in a solid, even though the solid is not crystalline. So atoms are packed in a certain regular manner, you will get a peak. And the intensity of that peak will depend upon R and Q. So this term here will no longer be non-zero. So you will get a diffracted beam. And the intensity of the diffracted beam will also depend on the orientation of the two atoms with respect to each other, because that is how the complete constructive interference or constructive interference will happen. So that will give rise to diffraction. So this is the principle of ABED. And here, the important thing is when you make the beam small, how many atoms are you actually sampling? You can have one cluster, you can have many clusters. If you have many clusters, then all the information from those clusters will get superimposed in your diffraction pattern, and it will be very difficult to interpret. Therefore, it's very important to have a very thin sample, and you should have fewer atoms being examined. This view-graph here shows the effect of the beam size on the appearance of the diffraction pattern. What you see is a selected area electron diffraction pattern, which we are all familiar with, taken from an amorphous material. Are you seeing this slide?
Yes.
So if you start making the beam smaller, you can see the change in the appearance of the diffraction pattern. From a ring pattern, slowly it becomes a spot pattern. And finally, when the beam is of the size of 3 to 4 angstrom, you start getting spot patterns. Remember, this is not a crystalline material. This is a amorphous material, but still you are getting spot patterns. That is because you are examining the symmetry of one cluster of atoms. So how do you examine one cluster of atoms or two clusters of atoms? That is very important. You cannot have 5 clusters together, because then you will have all the diffraction patterns superimposed on each other, and that's what is the result here, SAD, because you are examining many clusters at the same time. So thickness of the sample will become important, and this slide shows the importance of the thickness. So if you have a beam which is 3 or 4 angstrom in diameter, and if you have a thickness of 2 nanometer, then you will be actually examining about 20 atoms. That means 2 clusters. A very good situation. 2 nanometer thick specimen is not impossible to get. You can get. And if you have even a slightly broader beam, 5 angstrom in diameter, and after Gaussian spread inside this specimen, you will be examining about 50 atoms, so 4 clusters. It's still a manageable situation. That is because not all the clusters will be suitably oriented. So there are 3 things: thickness of the specimen, size of the beam, and orientation of the cluster, which will give rise to important information. So here we see the effect of the orientation. You can see that there are 3 clusters in the line of the beam, but only the middle one is oriented suitably, so it is contributing to the diffraction pattern. Then we see the importance of thickness. Here is a plot which shows the number of atoms being examined as a function of the beam diameter. If you have a very small beam, and even if you have a slightly thicker sample, you are actually examining a very few number of atoms. That means fewer clusters. Okay, so it is very important to have as you increase the thickness, the number of atoms being examined drastically increases, and that is not a good situation. So it's very important to have a thin sample, and also you need to have a very small beam, and also your cluster should be suitably oriented to give diffraction patterns like this, the way I've shown here. So how do you interpret the diffraction pattern? The diffraction pattern is interpreted in this case exactly the same way as it is done in case of crystalline material. Namely, you simulate the diffraction pattern using molecular dynamic simulations, and you get a simulated diffraction pattern, match it with the observed pattern, and if they are in agreement, then whatever structure you have simulated is the actual structure of the cluster. So we use a C++ code to develop a full 3D nano diffraction data from positions of for atom positions for any composition. A diffraction viewer is developed to probe the presence and arrangement of the quasi-crystalline polyhedra in the material. The object is to throw light onto the possible arrangements of various quasi-crystalline polyhedra that can make the glassy structure. So that is all about the background. Now we have our own result. This is in a multi-component glass where I show the observed angstrom beam diffraction pattern, and this is the simulated structure, and then we have the observed simulated diffraction pattern. There is very good agreement between the two. Then we have the this one. We have if you have a cluster you have already deciphered. Now you want to examine the relationship of one cluster with the next cluster. So if you want to do that, you have to make the beam slightly larger so that you examine 2 clusters at the same time. And then you get diffraction pattern, which is a superimposition of the diffraction patterns from the 2 clusters. Please note, this kind of experiment cannot be done in any other tool, where you want to know whether the 2 clusters are sharing their faces or sharing their edge or sharing their vertices. This is a very important information in understanding the structure of glass, because now you have started moving from the smallest building block, that is the SRO cluster, to a larger distance. That is how you are building the structure of the glass. You are going from short range order to medium range order domain. So you allow the 2 clusters to be diffracted together, and you get a diffraction pattern which is a little complicated here. The simulated pattern is here for a structure like this, and we could, after filtering this, we could see a match between these two, and therefore it was possible to say that this is how the two clusters are joined. So just to summarize this ABED part, angstrom beam electron diffraction, we could see how we can get information about a cluster. We could also see how the two clusters are joined, so that you get a good diffraction pattern from the two adjacent clusters, and tell how these two clusters are joined. That means you are building the from short range to medium range order, and you will see that this kind of information could not be achieved earlier by using tools like SACS or 3D atom probe tomography. Having moved from short range order, we now come to medium range order. And for medium range order, again, we have used a transmission electron microscopy based technique, which is again not very old. This is known as the fluctuation electron microscopy, where we make use of the diffracted intensity from clusters, medium range order clusters in the glass, and you get a diffracted beam, which is very feeble in intensity. So if you get an image, you will have speckles in the image, and this is actually the diffraction pattern. What you are targeting are the intensity diffracted in this region, which we never used to focus earlier. But in this case, we are actually talking about the intensity in this region. You can either use it in the image mode, or you can use it in the diffraction mode. In either case, this intensity is a representation of the medium range order in a disordered solid like this. So what you do is measure this intensity, and this is the first moment of the intensity, and this is the second moment of the intensity, and you get the variance of these intensities, which reflect on the medium range order in the material. So here we have used that information. We have two modes of fluctuation microscopy. Well, as I said, in either you can use the image mode, where you get the diffracted intensity in the dark field image, or you can use the diffracted intensity in the diffraction mode. If you are using the image mode, then it is known as the variable coherence microscopy. If you are using it in the diffraction mode, then it is known as variable resolution microscopy. So we have used both the modes of electron microscopy, and actually we observed in the glass, this is a glass here, that central region is having higher nano hardness, and as you go to the periphery, you have lower hardness. Similarly, we observed that this region has poorer corrosion resistance. As you go towards the periphery, it has better corrosion resistance. Everything is glass. Everything has the same composition. Then why this variation in properties? And that is because there is variation in structure, and that variation in structure is the difference in the medium range order, and that we could decipher by doing a fluctuation electron microscopy of this region, the middle region, as well as the central region. And we could show that this region, the central region, is more ordered. It's very similar to a crystal, whereas the region in the periphery is completely disordered because the medium range order there is poor. So that's how these are the plots from different parts of this glass, and which conclusively showed that the medium region is more ordered and the peripheral region is less ordered. So this is variable coherence microscopy showing the difference in structure in the medium range order domain. The more accurate way to do fluctuation electron microscopy is to use the diffracted intensity, not the image intensity, but the diffraction in the diffraction mode. We make use of the intensity. So here is the we do the same thing, that is get the diffracted intensity and make plots like this of the variance, and this is the observed variance. And again, we assume a structure of the medium range order domain and make a diffraction pattern out of that, and then simulate the fluctuation microscopy plot the way it is shown here, and match this plot with the observed fluctuation electron microscopy plot. And if the agreement is good, then whatever medium range ordered structure we have assumed is the actual structure prevailing in the glass. So this is for the first time that we have been able to decipher the medium range order to this kind of accuracy, which was not possible earlier. So from short range order, now we have moved on to the medium range order in the glass. So we are gradually building the structure of glass. So two components of the structure are determined. The third component is void, which needs to be determined. Just to conclude the medium range order part, comparison of theoretical and experimental reveals that the positions of maxima in the variance curves are in reasonable agreement. This signifies that the FPMD generated clusters arrangements over MRO length scale do approximate the real network structure. Domain size for this glass is self-consistently reproduced by FEM and NVED. The last part to be determined is the void. In crystalline materials, we have defects. We don't have voids, but we do have dislocations. We also have other kinds of defects, and they are very easily imaged in the diffraction in the dark field or in the bright field mode. You can also do high resolution, but you cannot do all those techniques in an amorphous material because first of all we don't know the structure itself. We are trying to decipher the structure, and any deviation from structure will be the defect. So despite these challenges, techniques have been developed to understand the nature of the open space or the voids in the amorphous material, and the technique that I am going to describe is known as the filtered high resolution electron microscopy. This is the intensity of the beam in the high resolution mode, and it comprises, besides other things, the projected potential of the crystal, which is most important, and that is actually reflects the structure of the material. In addition to that, we have other things like spearing function, interaction constant, and so on and so forth. Here we also have a component of effect of variation in the thickness of the foil. So if we use a filter, which is an annular filter, it may be able to filter out all this from the important information, that is the projected potential. And by applying an annular filter, it has been possible to reduce this equation to this form, where only the projected potential part, which actually reflects the structure, is depicted. So we use an annular filter by doing a reverse Fourier transform of the image. This is the high resolution image of the glass, and if you do reverse Fourier transform, you will get an image like this, where you have dots which actually represent the open space inside the glassy structure, and the white space actually represents the regions where we have medium range order and short range order. So if you see these black dots, they actually are the voids present in the structure of the glass. So the third component in the structure have also been deciphered. You can measure the size of these voids. You can measure the inter-void distance as well. So the best, just to conclude this part, these values are best interpreted by referring to the network where we have a wide volume fraction, which is shown here. The void sizes are shown here, and this is the peak of the void size, and this is the inter-void distance. And these could be correlated to the structure of the glass in a very nice way, and that is what is summarized here. The voids are present at the end of the clusters, that is the medium range order domains. This is the first time we are showing that the voids are present at the end of the medium range order domains. So we know how the short range order is there. We know how the medium range order is developed from that. And once the medium range order domain ends, we have the voids there. And then again, a new medium range order domain starts. So this is the structure of glass. And that kind of clarity has been obtained for the first time by doing a study like this. So just to conclude this part, I will just tell about the second point here. By employing diverse multi-scale techniques like these, it has been possible to reconstruct integrated structure of glass, unlike all earlier works on multi-component glass. The strategy served by complementing mutual limitations of individual techniques, corroborating common results, and establishing correlation between SRO, MRO, and free volume domains to be present. Most of these could be characterized structure for any multi-component glass. So this is the recipe for analyzing such complex structures, and we feel that this recipe can be utilized for studying other structurally disordered solids around us. That is, determine the short range order, determine the medium range order, and determine the location of these voids inside these structures. And then you can resolve many structures, not just glasses, many structures. And in this, the transmission electron microscope has a very important role to play. So I have just 2 more slides just to show the application of this. The first thing that we would like to apply is studying defects. that is defects in glasses. So these are this is an example of how the defects look like, and these are actually voids inside the region which is having defects, and the voids are much more in density here compared to the adjoining region. This kind of information was not obtained earlier, and here again we have voids. This is in a bulk glass and this is in a rapidly solidified glass. You can see the difference in the density of voids and the distribution of voids. And lastly, I would like to give this example where we are studying, as I told you, this has a very important role to play even in studying solidifications. So what I show here is a crystal and the glass next to it. As I told you, this glass was a liquid at some point of time, and once you cooled, it froze into the glass. But then this glass, whether is it similar to the glass away from the interface, where there are changes in this region just before it turned into a crystal. So that is the objective of this study, and this type of study again has not been possible earlier. Now that we see such small changes in the structure of glass, we can do such a study. So we found that the clusters near the interface, they are different in structure as compared to the clusters away from the interface. Okay, so before it forms into a crystal, the cluster changes its nature. It's possible that it becomes quasi-crystalline before it becomes crystalline. That is the aspect that we are examining now. Obviously, there is a change in the structure of these clusters, and we also see in the change in the medium range order as we move close to the interface, and that could also be shown. These are the results from medium range order determination, and these are the diffraction patterns obtained from near the clusters and away from the clusters, showing the inferences which I just mentioned. So with that, I come to the end of my talk, and I'm terribly sorry for the interruptions that took place during the presentation. Thank you very much.
Thank you. Gautam. Is there any brief questions? I don't see any hand raised, so Satyam, have you got any?
No, I just want to thank Dr. Dev for giving the insight into the ABED. That's a new technique developing. That's very nice to learn about the new technique. So just my congratulations for giving the technique.
Okay, if there's nothing, I think people are wanted to go for lunch. So, hello?
Yes, we are hearing.
No, there's a hand there.
Oh, yeah, Sandeep.
Yeah, this is Sandeep here. So, sir, how do you find the voids in the?
Yeah, you have to high resolution microscopy, and then you have to process that image by putting an inverse Fourier transform, and then you get so you apply the mask there by that process and filter out the information which shows actually the presence of voids. So voids are present, which are very small in size, which will be difficult to see otherwise. But you need to do this in a very thin region of the sample, and preferably done in a tiny microscope.
Done by Fourier filtering with the help of Fourier filtering. Okay. Okay, sir. Thank you.
Inverse Fourier filtering, to be explicit. Yeah.
Okay.
Okay, then. Gautam, thank you very much for this very interesting talk, because you are talking about new things, new way of looking at it, and I hope that this also can be used for crystalline materials, looking at the short range order.
Yeah, that's right. That many people have said that it can be used for studying clusters in crystalline materials as well.
I think we should do it. So then I close this session. Thank you very much, and hand over the mic to Professor Satyam.
Yes, sir. I think I thank the chairperson, Professor Kamani Chattopadhyay, and also the speakers, Professor Deepankar Banerjee and Professor G.K. Ray. I think this the standard of the talks are so high. I think many people will get benefited about the new techniques which we have given us. And I see already comments in the YouTube that they are enjoying the talks, and also they're very informative. So thank you all for being the panelists as well as giving this talk. I think because it's an online meet, we still go ahead and meet at 2 o'clock. So you can have a lunch on your table. So I think I last night came Muralidharan to let's start the session at 2 o'clock with Sridhar Rao as the first, Sridhar as the first one. So I hope this should be okay. Unless if somebody comments, then we can extend the time. So because so can we start at 2 o'clock itself? Okay, half an hour back, 20 minutes break is there.
20 minutes.
Yeah, because otherwise everything will get delayed. Some people may have planned to present some talks, they may not do it. Some issues will come up. Is it okay to start at 2, sir? Or shall we extend?
I'm
Yeah,
okay, yeah. If the speakers are okay, we can start at 2 o'clock.
So they can have lunch on the table, I think. Working lunch. Anyway.
We are at home. So.
Yeah, that's right. I mean, those who are at office also, it's fine. So I think Ashutosh, is that all right? We'll meet at 2 o'clock?
Yes. We'll start at 2 o'clock, right?
Okay. Thank you all, and let's break it now.
Actually, I sent my talk on PDF.
Yes.
It is better that you display from that side.
Okay, we'll do that. We'll take it.
Right now, system is installed in the Linux and PPT is in the Microsoft. It may give some collaboration. So I sent the PPT. So in case it is not, just ask him to call me back. In case you don't receive that,
I have already received it. We have seen it.
So let it display. PDF should be displayed from your side.
Sure. We'll take care. I'll take care of it. We'll take care of it. Thank you.
Bye.
Oh, okay, so let's meet at 2 o'clock. Thank you. And
thank you, Kamanyo.
Yes, sir. Thank you all.
Thank you.